Morning, everyone. Welcome to this last day of PFDM 2023. My name is Cesare Sangiorgi. I am your chairman this morning. I'm sure you had a great evening and I hope enjoyable night. Although the food that we had, the great wine, and the people, of course. I think we all need to thank Professor Pereira and Elisabetta for what they gave us last night, including very good dancing. So we found that Professor Pereira is also a very good dancer, indeed. And so I know it's early, Saturday morning, but we need to start our session that is devoted to surface distress prevention and management. This session will see an invited lecture plus 4 presentations. So without any further ado, let me call at the podium Professor Gerardo Flinch from Virginia Tech Transportation Institute. Professor Flinch will talk us about pavement friction management. I also have here a few words to say about Professor Flinch. He is the Dan Platt Professor of Engineering with the FIA Department of Civil and Environmental Engineering and the Director of the Center for Sustainable and Resilient Infrastructure of the Virginia Tech Transportation Institute. He chairs the TRB Standing Committee, AKP10, on Pavement Condition Evaluation, as well as the World Road Association, PRC, that we all know, the Technical Committee 3.3 on Asset Management, and he also serves as Vice President and Technical Director of FM Consultants, LLC.
Thank you very much.
Yeah.
And good morning, everyone. Let me start by congratulating the organizers for a great conference and thanking you one more time for giving me the opportunity to present some of our recent work. And it's a topic we've been working for a few years on the link between pavement engineering and safety, and in between also all the maintenance and operations in a way. So the presentation will start with a very brief introduction that I will go fast because we cover 90% of that already in some other presentations as an advantage of being towards the end. A lot of things have been already presented. A little bit of overview of experience in the last few decades in the US in regards to safety and friction, and then focus on one of the projects we just completed on developing crash modification factors to quantify the impact of friction and microtexture improvements on crashes. And then a few other relevant efforts, just for your information, that we have completed recently or we're doing, and then a few comments to finish the presentation. So a lot of acknowledgement that there was a big group of people who work in this project. You have the names there, and then the Federal Highway was the sponsor through Andy Mergenmeyer and Chef Shaw that are our key contacts. But there's also a lot of information from other organizations, some of the pool funds we've run over the years, and of course our research group and CHRP and ERPAC. So to get started here, maybe we can go a step back and think a little bit, well, why do we build roads? And maybe what the user wants or expect from the road. And very early on, we built roads to provide mobility and access. And we wanted to go from A to B throughout the year without getting stuck in the mud and so on. But of course, that's not enough today. Today, our road infrastructure has to support this mobility and access, what we had to do with comfort, with safety, fast and reliable travel, with the energy efficiency, low pollution, low noise, low environmental impacts. We're looking for sometimes even some energy generations, renewable material. And of course, we also reflect all of these things in performance measures or level of service that we set for our roads, for our assets in general, or our transportation assets. And the last few decades, we put a lot of emphasis again on the user, how we can make sure that the road infrastructure, the transportation infrastructure in general, provides a safe, comfortable, reliable travel for everybody, both for people and for goods. And the current, well, not anymore, but the recent problems with the supply chain shows how important it is for our daily lives. And of course, if we need to do that within the context of a sustainable infrastructure, sustainable development, that where our decisions are guided by three basic principles: promote social equity, economic development, and environmental protection. So we have these three pillars of our sustainability, and then our decisions are guided that way, and then the pavement surface properties, in a way, is what is impacting all these things that I was mentioning earlier, and again, that we reflect in ways to measure. We call it performance measures, key performance indicators, level of service, etc. But the idea is we develop some indicators that allow us to follow the performance of our road. And within this big list of indicators, provide a safe pavement is an important part, and that's where the friction plays a very significant role. And we covered already this. Friction is just the coefficient of friction is the resistive force when we're trying to stop or accelerate, divided by the weight that is the load that is placed on the wheel. And when we look at it from a physics point of view, we try to separate it between two components, although it's a continuum, but we say there's some adhesion going on and then some hysteresis. And these are related with two key pavement properties that impact this skid resistance of friction. We have the microtexture, usually provided by the aggregate, and again, good quality aggregate is fundamental to provide long-term friction and skid resistance, and also the macrotexture that help with the hysteresis, as well as allowing the water to drain when it gets pushed between the pavement and the tire when we're driving on a wet pavement. So with that in mind, we have two properties that we have to measure, and we know that those two properties impact friction, and as we talked about yesterday and in some of the other presentations, they impact the way we accelerate, the way how long it takes for us to brake, how well we can keep control of our vehicles when we are maneuvering on a curve, etc. So in the US, we do have quite a bit of experience with friction and safety. And going back to many years ago, in 1973, some folks published work on the relationship between friction and crashes on wet pavements. And we see here as friction increases, the number, the skid number is in this case, but it's friction. Friction increases the number of crashes, the rate of crashes go down. And what we learned in the last few years is, well, that wet crashes do increase when friction is low, but also the dry crashes also are impacted. Although we assume that dry pavement for many years thought that, well, the pavement is dry, it's okay, we don't have to worry about friction. We did find a stronger statistical relationship between dry crashes and friction, so both play. And then the other thing is there are many different types of equipment, and since we are looking about a property that is conditioned by rubber skidding on a pavement or on a wet pavement, depending on the type of rubber you have, the type of equipment, what is, if you lock the wheel or if you slow the rotation, etc., there's different technologies. And again, for many years in the US, we mostly use a lock wheel trailer, but in the last few years, we've been moving to continuous friction measurement because that allows us to be more proactive in the way we assess our network so we can focus the friction improvement efforts in areas where there's, for one side, higher demand for friction, and the other hand, where we can detect supply at a very, at a high degree of resolution, so with this continuous equipment. So in our case, we've been fortunately to have support from various states through the years, starting in around 2007. We created a series of pool funds. This is our collaborative projects among states. And we are, the first two phases focus a lot on the equipment comparisons, trying to match things, technology evaluations, and as part of this, we run like a loan program where we bought some continuous friction equipment and we lent it to the state to test it and try it, and we train them how to use it. We leave it there for a few weeks, and eventually the technology start to pick up. Of course, all of this was supported by Federal Highway. Then the current third phase that started about 2 years ago now, the number of states have been growing that are interested in this, and we are focused on implementations of this result as part of the asset management process. How we can integrate the safety management with the pay management and making sure we optimize our road investment to maximize all the different performance indicators, including safety, in addition to the more traditional condition-based indicators of IRI and pavement condition, surface condition, and so on. So we are looking into creating this link. And of course, this is not news. There was an NCHRP project a few years ago that started to kind of promote this, this approach, emphasizing again that there's a relationship between wet crashes and friction. That one of the things that introduced, mostly following the lead of Europe, is that the need of defining friction demand categories, because you don't need the same type of friction on a freeway that you need on a local road with a lot of curves and intersections and so on, and you don't need the same friction on a straight segment of your road than on the curves and the intersections. So that was one thing. Then there's the idea that we can manage the friction so we can be proactive and try to find places where we may have accidents because of lack of friction, where the offer, the supply doesn't match the demand in that particular location. And in particular, this guy talked about investigatory and intervention levels. And also emphasizing something that wasn't new, but maybe wasn't as well as defined before, is that we have to design the surface of the pavement to provide good level of friction, not just when the pavement is new, but throughout the life cycle of that surface. So that guide was developed again around 2009, was approved by Ashton in 2010, and there was a renewed effort on the need to do this. At the same time, Federal Highway felt that it was important to kind of maybe look at the different technologies that the ones we were used. So there was a project that we were lucky enough to win with several partners, including TRL, Applied Pavement Technologies, and a few in the Virginia Transportation Research Council, where we were tasked with develop investigatory levels for friction and macrotexture for different type of roads. We collected data, but we also bought continuous friction measurement equipment. We bought the SCREAM system after a careful review of all the available technology. We wanted something that was proven. SCREAM was used a lot around the world, so we thought it was a good way of doing that. That project resulted in a couple of reports, one that showed the benefits of this continuous friction with respect to traditional lock wheel system, that because of the way it works, we cannot test continuously. We may test maybe a couple of tests per kilometer, 2, 3, but we don't have full coverage. And usually the operators don't brake in the worst conditions where you have intersections or you have curves, because they are afraid they may lose control of the trailer. And then there was another report where we did some harmonization between the SCREAM and the previous devices that were used, lock wheels, just to allow the agencies to use the previous experience. And at the same time, we developed a standard that's been approved by AASHTO to measure continuous friction on a control conditions, and we have a slightly different measure than the one used in the traditional by the SCREAM. We call it SFN 40. We measure at 40 miles per hour. It's a little bit higher speed than the typically used for the SCREAM. But there was a few interesting things that came from this project. One of them is confirm some things that have been observed, but maybe not in a very systematic way, that both wet and dry crashes can be reduced by improving friction and macrotexture. We also started to explore the use of safety performance functions that include friction and macrotexture as part of the variables, so we can then estimate how many crashes we can reduce if we improve the friction by 5 points or 10 points. And we developed some approaches figure out what level of friction I should be looking at, below which the crashes may start to go up, and that's what we call investigatory levels. And we kind of got rid of the intervention levels. No agency will just go and fix a pavement because the friction is low. Most agencies, what they do is they trigger an investigation and then figure out if that low friction is contributing to crashes or not, because not in all cases, if the speed is low and there's not a lot of demand for friction in that section, that may not be a good investment. And finally, the importance of measuring this continuously, and so we won't lose those areas where there's localized problems of low friction that are crashes, and maybe if we do one test per mile, as many agencies did, we won't see it in detail. And that brought us to the current project that I will expand in a second, that the idea was, well, we have these 4 states where we collected data as part of the demonstrations. We have a few others that asked us to collect data for develop kind of pilot management projects, including Virginia, where we did a significant part of the network, about 9,000 kilometers. And and then apply in a systematic way the procedure used in the highway safety manual that the AASHTO has, applying develop safety performance functions and empirical based estimations to find out how many crashes we can expect at different type of roads, and also if we improve the friction, what will be the impact on those crashes. And then we had assistance to our implementations. We've been demonstrating, again, the equipment in a few other states and then making products kind of to promote this approach. So one of this product was a revised guide for pavement friction that was approved last year. And it's mostly based on the work on the last two projects that I mentioned. And has a few modifications from the previous. The first one is, as I mentioned before, the focus shouldn't be only on wet crashes, because although the influence on dry crashes is a little bit lower, we had many more dry crashes than wet crashes. So the impact of improving friction is much more significant if we really look at all the crashes, and I'll show that in a second. Then the importance of continuous friction and macrotexture measurements. We got rid of the intervention level. That's something that the state didn't like. They didn't want to say, well, I have to do something. The idea is if the friction is relatively low, I should go and do a safety investigation and decide whether or not the friction improvement is needed. And then we incorporated a cost-benefit approach for prioritizing safety enhancements. So if we know how much the treatment costs, we know how much the friction and macrotexture will improve, we can see how many crashes we can save. We can put a value on those crashes, and then we can say those are the benefits, and we have the cost, so we can prioritize our safety investments by the highest benefit costs involved. So going back to the focus of the presentation, the report is not available yet. It is finished, but these days we had to make it kind of 508 compliance. They call it, is to be accessible for everybody to read. So it has to have some special features, and then this usually takes a little bit to get all figured out. But all the information has been approved. It's just a matter of formatting. So the idea is that we got all the data we had until then, where we started with the type of facility, and what we did there, we used the facilities that are used for the highway safety manual from AASHTO, and collected the crashes by type, and we did dry, wet crashes, and also the calco is related with the severity from damage only all the way to fatalities. And we collected the friction surface characteristics, the pavement surface characteristics, friction and macrotexture. We truly didn't collect it as part of this project. What we did is put all the information we have collected since we got the SCREAM together into one database. And then based on that, we studied the relationship between friction, macrotexture, and crash modification factors and safety. So what we did is we developed safety performance function. This is just regression equations that relate all the road variables, including friction and safety with an expected number of crashes. We tried three different models. We have Poisson model, negative binomial, and the negative binomial with the mixed effects. And we select the best one, and based on that, we develop crash modification factors and what we call crash modification functions, because now it's a continuous. We know for each 1 point improvement in friction or macrotexture, how many crashes we can reduce. And so when we put everything together, we have about 8,000 kilometers of roads from 5 states that over the last 3 years had about 160,000 crashes. We only use roads that have not been treated in the last 3 years, so we can have a good estimate of the crash that happens and on top of that particular pavement there. And we had the 4 categories of road: freeways, arterials, and those we separated between divided and undivided, with rural multi-lane road and then 2-lane roads, two-way 2-lane roads as the lower category. The dependent variable was all the crashes, the wet, the dry, and then the fatalities and severe injuries, and also property only and so on. So, and then the predictors that we used in the equations was, of course, the traffic, because, of course, the traffic gave you the exposure. The higher the traffic, the higher the crashes. We use a state variable to differentiate conditions within the state, the facility type and site type, and this was just a straight segment, a curve on an intersection, or if it's a freeway, access point for that freeway, because in those cases there's more maneuvers, so you have a higher demand for friction. We have surface type, macro texture, friction, grade, cross slope, and super elevation and curvature. And all of this information is collected in one pass with the screen that we have. It's a multifunction. It has an inertial system that allows us to get the surface of the geometry of the surface of the pavement too. So all of that information was compiling in the database, and if we look at here just for illustration purposes, this is all the data for the freeways, the interstates. You see there's a distribution of friction, and then you have here the crashes, and then we have the same scene in this case for the urban arterials. There's a few less miles. You see that the average values for friction and macro texture are similar, but the trends, the trends for how crashes increase as friction decreases is a little bit more significant. It's a higher slope for the urban arterial, where there's more conflict, there's more demand for friction than in the freeways, where the geometric design is good, so you have a little bit less demand. And again, this is not new. The initial work on this was published in the UK many years ago, but we kind of confirm it with our own data. So then what we did is we start to run these models, and not all the variables were significant in the models. We try again the Poisson model, the negative binomial with mixed effect. The mixed effect was to account for the states and the road categories or the types, and then without the mixed effect, quantify the impact of each type of road. And we compare the statistics, but if you look at here, in all cases, the coefficient for friction and for texture is negative, meaning the higher the friction, the higher the macro texture, less crashes. So that's good. And then if we consider the mixed effect of this, it was almost no different. So we decided to use a negative binomial model that is basically an exponential model, where the log of the crash count is given by a function. It's a linear regression when the variables are converted. You have the friction, you have the log of traffic here, because this is end up being multiplicative in the model, and then all the other variables. It's just a regular negative binomial regression, and then we run this for each row category. And then this is an example here for freeways. Again, you have all the coefficients for the regression, the standard error, and then the 95% confidence interval, and the p-value. You see it in this case, all the variables are significant, except for the curves. And then we have some goodness of fit statistics there. But I think that the important part to look at here is, again, there's a negative coefficient for friction, there's a negative coefficient for macro texture, showing that statistically there's a relationship that is statistically significant between the crashes and the friction and macrotexture level that we measure. And again, we did this for all the categories and all the types. And again, the type is breaking down in tangent, meaning straight segment, ramp access point curves, intersections in the other cases. And then for each of these, if we divide the safety performance functions for a particular level of friction versus a baseline, all the other terms cancel. So what we have is we have an equation where the crash modification factor is a function, an exponential function of the change in friction, and the same thing for macrotexture. So then what we can say, well, if we reduce, so if increase friction by 10 points, my crashes will be 90% of the crashes I will have in the current condition. So I may be able to save about 10% of the crashes. And that's significant because in the US we have 43,000 people that die every year because of crashes. So if we reduce 10%, that may be 400 people that will not have to die because of this. So in addition to all the damage and all of that. And if you see for higher demand categories, the values increase, and I think it's easier to see it in a graphical way. So this is the overall trend. This is the crash modification factor. This is the number you are going to multiply your crashes today to get the crashes you'll get after you improve the friction or macrotexture. You see that the friction improves, the value goes down, meaning you save more crashes. If you look at the freeways, the reactions are not that great. Again, this is similar to what's found in the UK. But when you get to urban arterials, that's the highest value. You see 10 points, you save about 25% of your crashes. Then you have the rural multi-lane highways and the rural two-lane, two-way highways, all of them gave you roughly a distribution of a potential reduction, of course. This is all estimated by the mathematical model, that you could say maybe between 3 and 25% of the crashes. But if you focus on the high demand areas, for example, the urban arterials intersections where there's a lot of conflict because there's traffic on peak hours and so on, so there's more potential causes of crashes, you see there that you may be able to reduce up to 30% in that cases with a 10-point increase in safety. And that's not a lot. This is just maybe replace a pavement that's been polished with a new pavement even with the same surface. If you have a high friction surface, you may be able to increase that by 30 or 40 points. So you see there you reduce maybe less than half the crashes you have. And if you look at some of the work that Federal Highway has done in that area, there's been some significant proven number of crashes that have been reduced. Similar issue for macrotexture. Here, of course, the scale is a little bit different. So if you think maybe increasing 5.5 millimeters of macrotexture, that's usually macrotexture is start 0.5 to 0.7 if you do a dense mix. If you put an SMA that may have 1.2, you may be able to reduce the potential reduces in crashes somewhere between 4 and 11%. And this was significant in most categories of road. In the rural two-lane, two-way highways, it was not significant. Maybe because of the sample size that wasn't that big, maybe because the speeds are lower, and macrotexture is more significant when you're driving fast. But again, some proven numbers. We also look at by type of crashes. Here we have, you see the dry and wet crashes. The wet crashes are reduced more, and we knew that. And if you go to urban and suburban arterials, you have the same type of trends. But again, you can prove that you can reduce both dry and wet crashes by improving the friction of the macrotexture. We also did it for fatalities and serious injuries, but that was always showed reductions, but it wasn't very stable. So we don't recommend to use. We may need to collect more data. Only a very small percent of crashes result in fatalities or serious injuries. So to get a representative sample, you need a bigger network of data collected. Right now, there's a few states that are collecting that. So instead of 8,000 kilometers, the new database may have 25,000. So in that case, maybe we can get better statistical relationships there. So that was one part of the study. The other part said, well, can we define levels of where we can say the friction is too low, in the sense of that may warrant an investigation to see if it's contributed to crashes. And for that, what we use is the charts I showed you before. We plotted the distribution of friction. You have the friction here, so you see this is the distribution for all the pavements on the freeways that were measured. And here you have the crashes. And we did a little bit of a smoothing of the trend just because of the random natural crashes. We adjusted a little bit. But you can see here is, so if you look at the dots here, this is the crash rate. How many, for all the rows, I have between 40 and 42 friction number. We look at the crashes, we look at the length and the traffic. So we can get the average crash rate per 100 million vehicle mile travel. So it's a measure of exposure in a way. So you see here that for high friction, there's a kind of lower value of crash rates. And of course, there's always an increasing trend. There seems to be a more uniform. Of course, you can argue that there may be different points, but then when you get very low, you have more crashes, a higher rate of crashes, and you have also more dispersion because we have less section. But kind of subjectively to some extent, we call it graphically, we define a value that we consider reasonable. And we say with a friction number of between 36 and 38, we use friction number instead of coefficient of friction, but that's just 100 times the coefficient of friction. This is tradition in the US with the log wheel, that's what we've been using. So you see there's a value. We did this also this is for tangents in the interstates, in the freeways. If you do it at the access points, if you look at the crashes are higher, the rate of crashes are higher, you have more conflicts between vehicles, so you demand higher demand. So if you start to look at it's less obvious in this case, but you can have a slightly higher value there compared with the value you have when your friction demand is lower in a tri-segment of the road. And then we repeated this for all the different road categories and site types and develop a table where if you see here when you have a higher demand, for example, a multi-lane road without control access compared with a freeway with control access, you need more friction because, again, you have more interaction between the vehicles. We also did an equivalent to compare it with the UK standard, and the values we got were very similar. The reason why we need to do the conversion is because we run at a different speed, and we also did not use a correction factor that the UK uses to go back to a different type of rubber they use when they start to measure friction with the screen. But if we made the conversion, the values we obtain, if we divide by 100 and do the conversions, are very similar to the one in the UK. And the other important thing is that within the same category of road, for example, a rural two-lane, two-way, when you get to curves and intersection, you need more friction. So the threshold is higher. So the friction you're providing in the tangents may not be enough in some curves and intersections. That's why we are looking into putting high friction surfaces in some of those areas. And one of the things that came from this is that the Federal Highway has included continuous pavement friction measurement as part of what they call a proven cross-cutting safety countermeasure, meaning these are treatments or activities that can be included in the highway safety improvement program. That's something that each state has to do periodically, every 4 years. Sometimes they do it a little bit more often to show the Federal Highway how they are investing their safety funds that came in a separate line item. So that's why many states are looking at this more carefully, because they have a special pot of money that can be, of course, they can be used to improve signs or maybe do other things, but they can use to measure friction continually and do high friction surface, etc. And again, it's important to keep in mind that we are working on a safe system approach where we want to have this safe roads, safe vehicles, safe speed, safe users, and careful on some crash points and so on. And both wet and dry crashes can be reduced by friction management. So it's a proven countermeasure, as I said before. And one of the downside, in a way, something that is a difficulty we've been facing, is that it needs some multidisciplinary collaboration, kind of breaking the silos within the DOTs, because you need the payment folks that usually is within the material area in the US. You need the safety folks and you need the maintenance folks. So they have to be talking to each other. And of course, the programming division. So there's a lot of groups that have to work together. Very quickly, a few other relevant things. We recently, in the last couple of years, finished an NCHRP project to develop network level macrotexture measurement standards that have been proposed. These are not approved yet, but they should be approved this summer, hopefully by Pierre. One of the things we recommended there also is that if you want to measure macrotexture in all type of pavements, we should put maybe a line laser oriented at 45 degrees. Maybe the 3D systems will be the future, but based on the technology, that's what we've done. So we just retrofitted our screen with that last week, so we're trying it this week. And then we also recommend some of the same things that was mentioned in the couple of presentations already, maybe looking at envelope profiles to get maybe a better indicator of macrotexture than the MPD we have been using. We also had another NCHRP project to develop models to predict and mitigate hydroplaning, and that's available. And right now we are working with Federal Highway on another project to kind of try to design the mix to have appropriate macrotexture. And again, we just finished a first phase. It was kind of a try with data from 3 states, and we are doing a national validation that started this month. So, and then looking at the future, we've done some work on measure the friction with vehicles, just using the information from the sensors in the vehicle. We had some funding from the National Science Foundation to do that. And right now we are starting a pool fund, very recent, where we are looking about this information and how we can incorporate the information from the vehicles. In addition, maybe other sources like instrumentation and BIM during construction as part of the asset management process. This is just was approved for a start maybe a week ago or so, so we haven't started, but we got to go ahead. So to wrap up, because about the time, the idea is that these studies that we mentioned confirm a strong statistical association between pavement surface frictional properties, friction and macrotexture and crash rates, and higher friction or higher macrotexture result in lower crash rates on all roadway types and facility types. One of the things we haven't looked at in spending is that truly the friction and the macrotexture are not independent. Because sometimes when you increase the macrotexture, you reduce the contact between the tire and the pavement, so the friction may not be, maybe a little bit lower. So we need to study that interaction, but we haven't so far. It's possible to develop safety performance functions for crashes on different roadway facility types that include friction and macrotexture. And that allows us to quantify the friction and microtexture impact on the potential crash reductions you can have when you do a resurfacing on your pavement. And for most categories, both of them were significant, except for the case of two-lane, two-way roads where the microtexture was not significant in this case. We think it may be that the database is not that much. Few states gave us roads to test that were not in the first three categories. These safety performance functions allow us to develop crash modification factors and functions, and that's what allow us is to quantify the impact of different pavements improvement on the crashes. And in some cases, we were able to find up to 30% reductions on urban arterial intersections. So that's a significant number of crashes that can be reduced. And then the data also allow us to define what we call illustrative friction investigatory thresholds, because this is, you have to put a little bit of a policy to really define those carefully, because it's in some cases you don't want to put it too high because a lot of your network will fail. So you have to do a little bit of balancing between something practical. And again, these levels of investigations are higher for higher friction demand sites. Again, this is not new, but it was confirmed with our data. And then the final note there is that incorporated friction management into asset management is a multidisciplinary effort where we need a lot of cross collaboration between different areas within the Department of Transportation. And again, this is in general for asset management, but it's been a challenge for the safety improvement, because at least in the US, the safety office handles the safety money and the payment office handles the payment resurfacing, and how we put it together so we can prioritize areas where the payment needs repair and friction needs improvement for safety. So we can focus our investments where we can get the most payoff for the various performance indicators we are trying to achieve. And that's all. Thank you very much.
Thank you very much, Gerardo, for your insights in pavement friction management. I think we all understood that having data is basic. If we don't have data and having such an amount of data, I think is amazing. I don't think we can make this in Italy. To have this amount of data and put all this together, it will be a dream for us, actually. So congratulations. Thank you again. Now we are calling our first presenter this morning, who kindly agreed on just pronounce his name, as the surname is quite difficult for me. That is Paul Latab.
Yes.
So welcome, Paul Latab. Paul Latab is going to talk to us about International Friction Index. The floor is yours. 15 minutes, please.
Well, thank you very much for giving me an opportunity to be here. Today, I'm going to give a presentation about International Friction Index prediction with machine learning for pavement management system. This is an overview of my presentation. First, I'm going to talk about the background on skid resistance. And I would say I just do a recap because on the first day of the conference, a lot of people talking about this topic before. And the second topic that I'm going to talk about is the existing pavement management system in Thailand and the objective of this study. The next will be analysis method based on the machine learning algorithm. And then I will talk about the result. And I will end my conclusion. I will end this presentation with conclusion. So let's do a recap on skid resistance. On the very first day of the conference, a lot of people talking about this topic. So just do a recap. Skid resistance or friction is an important characteristic of road pavement, and we all know that with low skid resistance, it can lead to an unsafe driving condition. And there are four main factors affecting pavement frictions. The first one is pavement surface characteristics, such as micro and macro texture and material property. We all know. The second factor is vehicle factor, which depend on vehicle speed and driving maneuver. The third factor is tire properties such as tread design, tire pressure, and the last factor that affect pavement friction is environment such as temperature and surface water. In order to determine skid resistance, we have to know both micro texture and macro texture. For micro texture, it depends on surface characteristic of aggregate, such as angularity, surface texture, and aggregate shape. For the macro texture, it depends on the property of asphalt mix, such as shape, size, and gradation of aggregate. In order to measure frictions, we have to use some devices, and these devices can be classified into two main categories. The first one is high-speed friction measuring device, such as lock wheel, side force, fixed slip, variable slip. The second category is low-speed friction measuring device. I think we are common with it, the British pendulum tester, dynamic friction tester. With the friction information combined with the mean profile depth, we can calculate international friction index. Let's go back to Thailand. Okay, in Thailand we do have some device to get the information regarding international friction index. We use fixed slip friction test, just like what I show you on the slide. And we also use a British pendulum tester to get the information regarding friction. And we also do the sand patch test to get the MTD. Combine these two information, we can calculate international friction index, or IFI. For the existing pavement management system in Thailand, our country, we have our own pavement management system called TPMS, or Thailand Pavement Management System. It is pretty much based on the HDM model by the World Bank, but we modified a little bit to suit Thailand environment and requirements. However, the friction prediction model has not been incorporated into the TPMS yet. So that's why this became the objective of my study. We try to develop pavement friction prediction models based on machine learning techniques such as neural network, random tree, random forest, and also we use conventional multiple linear regression as a baseline for comparison. For this approach, we just let the data tell the relationship. Okay. From the database that we collect regarding pavement frictions, on the table you see here, we have some input, and the output is going to be international friction index. Let's talk about the input. The input that I use in this study, I use MPD. I use the surface type, which is categorical variable. It can either be polymer modified fault, asphaltic concrete, para rubber modified asphaltic concrete, para rubber slurry seal or slurry seal, age of the pavement in days, number of lanes, and also aggregate type, which is categorical variable. It can either be basalt, limestone, or andesite. And the rest of the input are traffic-related variables such as AADT and amount of trucks, different category of trucks per day. With this information, we input it into a machine learning algorithm to predict international friction index. In this study, I consider 4 models. Each of them has their own advantages and disadvantages. Let's start with the first one, multiple linear regression. Multiple linear regression is based on minimization of square error. It is simple to implement, and it is also provide causality between input and output. We can explain the relationship between input and output very easily. Going to use multiple linear regression as the baseline model for comparison. However, it has some limitation because it has less predictive power. The second model that I consider is neural network. It is based on interconnected neuron, and we try to calculate the weight between each pair of neurons in the network. Neural network have a modeling capability for nonlinear system. However, it's quite difficult to explain the relationship between input and output. It's quite difficult. And also, sometimes we come up with overfitting problem for neural network. The third model that I consider is decision tree. It is based on tree structure and data partitioning. This type of model is good for categorical data, and it requires minimal memory usage. But it has some limitation because sometimes it's more data dependent than the random forest. The fourth model that I consider is random forest, which is an extension of random tree. In the random forest, we just have several trees. Then we use the bootstrap data to each of the tree in the forest, and each of the tree will provide the estimate, and then we calculate the average of the estimate from all the tree in the forest to get the estimate for the random forest. This is the way we do it in random forest algorithm. It's also good for categorical data. It can minimize variance, but it takes more time to train than decision tree. The data that I use in this study, I divide the data into 2 sets. The first set is trained data set, and the second one is tested data set. And for the neural network, decision tree and the random forest, I do the principal component analysis to reduce the number of variables. And the variable that we kept will be at the 95% variance. There are some results, okay? The first row of this figure represents record number, where I plot the true value of international friction index with the predicted values. The blue dot represent the actual international friction index, and the yellow dot represent the estimated. Okay. The second and third row represent the relationship between predicted and the true value of international friction index for the trained data set and tested data set. And the last row represent R-square. I give the R-square information. The first column is the result for multiple linear regression. Second column is the result from neural network. The third and the fourth are the result from decision tree and random forest. Okay. After we do the calculation, The multiple linear regression gives the R square of around 0.15 and the R square of around 0.47 or 48, while decision tree and random forest give the R square of around 0.7 to 0.75. So based on this study, we found that decision tree and random forest are more appropriate to be used to predict international friction index. Let me conclude my presentation. I would like to say that skid resistance factor is an important factor that should be incorporated into pavement management system. But now at the time, back in Thailand, we don't have that kind of model yet. That's why I try to do this study to come up with a prediction model for international friction index. And in this study, I compare 4 models: multiple linear regression, neural network, decision tree, random forest. And there are 2 types of data that I use: categorical data and also numerical data. The data are divided into 2 sets: trained data set and tested data set. I also use PCA technique to reduce the number of variables. And what I found here is decision tree and random forest are the most appropriate for predicting international friction index. It's pretty much it for what I have. Thank you very much.
Okay, thank you very much indeed, Ponteleb, also for being right on time. And so we are kind of on schedule. We also understood again how data are important to also in the analysis, this kind of analysis that's preliminary as I see, but it's going on, right? The next presenter is Maurizio Bonate. I see Elisabetta here, so okay, Maurizio is coming, who is going to talk about PMS and TMS.
Good morning, everyone. I would like to start this presentation by thanking the last 2 presenters to make my job here today easier, as you're going to see during the presentation. So my name is Maurício Bonatti. I'm here today representing this research group from University of Minho, namely from the departments of civil engineering and departments of informatics. In this presentation, I would like to explain our idea about PMS and TMS integration. And this presentation is also part of the dissemination task of the European project InfraHub. So for this presentation, I'd like to give just a brief introduction about the InfraHub project, then explain our PMS and TMS, and then finally our idea about this integration. So for the InfraHub project, we know that 4% of the accidents take place inside the work zones. So this means that your workers are exposed to significant risk of accident. And many of the maintenance interventions in the pavements are repetitive, so most of them could be replaced by robots or automation systems. So the idea of the project is to boost these introductions in the road management. And the mission of the project is to increase the safety of the road users and the workers, and while decreasing the cost and increasing the availability of the transport network. So let's talk about now the PMS. The PMS has 2 main objectives. The first one is to assess the consequences of these robots deployments and also to monetize these deployments as well. And this work package is divided in 4 tasks that I'm going to explain now in the following slides. So for the first task, we are going to model the maintenance intervention process. And by this model, I mean to describe all the operations during this process. And to help us during this modeling, we are going to use the business process model notation methodology. And here, we have the 8 models that we are going to develop. 2 of them could be classified as preservation activities, 3 as our rehabilitation activities, and we also have 3 models that we consider relevant models. Here we have an example of one of these models, is the crack filling model. As you can see, the workflow of the activity, we start from the request of the activities, and the transportation of the crew, closing roads, then we have routing, cleaning, and so on for the activity, then open again the roads, and then come back with the crew to the head station. For the pavement management service upgrading, as we just listened to our last presenter, we are going to perform some predictive modeling based on our indicators. Most of these indicators are from the cost action 345. That is most squid resistance, longitudinal and transversional evenness, bearing capacity, and surface damages. And for these models, we are going to consider the traditional one, that's Markov models, and then neural networks, and random forest model as well. Here we have just an example of this, the results of one of this model, the degradation performance prediction. And we are also going to consider not only the prediction of the damage, but also the recovery of the performance of the pavement after the treatment. And we are going to consider here 2 scenarios. One, that is the treatment is made by a traditional way with humans, and the second one that is based on a robot's intervention. Our third task is to perform a cost analysis to compare the traditional way of doing maintenance in this new way using robots. And finally, we are going to model the decision-making process by taking into consideration the performance of the roads, the costs associated, but also the safety of the road users and the workers. I'm going to explain later. And also the traffic time. So now regarding the TMS. In our TMS, we aim to install a traffic coordination between the robots and the road sector, and also to analyze the safety impact of this robot deployment. And the work package is divided into tasks. The first one is to implement a V2X communication, and the second one is to analyze this road safety. Here in the image, we have an example of how this V2X communication works. So as you can see, we have the communication between the machinery inside the work zone. We also have communication between outside the work zones to the work zones, and we have a drone over there that I'm going to explain. So let's imagine 2 examples here. The first one is that you have a machinery that is going outside, from the work zone to outside of the work zone, and then we need to communicate this to the road user so it can reduce the velocity. So this communication can help this. Another one is we have a road user that's supposed to be on a left lane of the road, but he is in a right one. So we can communicate the work zone that this driver is coming, could be faster, but he is in the wrong position. We know these variables because about using this technology, V2X, nowadays in Europe we have less than 10% of the cars has this technology. That's why we have the drone over there that can help us to monitor the position and velocity of these cars as well. And then for the second task, we are going to analyze the safety by consider the safety-related issues, and our objective is to find the key points that could help us during the decision-making process. For the road safety analysis, I was mentioned in the first presentation, you have many variables, such as geometric and geographic, and here could give an example. For example, if you have a straight road where you have a work happening there, and then you have a work happening in a curve, so we have 2 different scenarios where the safety could be different between these 2 scenarios. And also here we have an illustration how this modeling works. So you have the geographical area with the traffic routes. You can see the vehicle communications between the work zones and also the cars and the transportations. We also have RSU, that is signs to the roads. And our objective as well is to define an area that we are going to broadcast this message. This is also a variable in our work to determine the radius of this broadcasting. So for the PMS and TMS integration, our objective here is to create a loop from the PMS to the TMS and the TMS to the PMS. For example, the PMS can predict the skid resistance of the roads through the years and then use this as an input in the TMS. The TMS can evaluate the safety and also the time metric of the road, then give back this to the PMS. And then the PMS make a decision or also run another prediction for another year. And then this loop happens until make a final decision when we should do the maintenance interventions. We don't have here so far results of these projects. We still are compiling our results, but I would like just to bring some information. We know that the introduction of this robot is going to be a challenge for the TMS and the PMS. Another issue that we're going to find in this project is we don't know if the robots' information are going to be available, so you can compare our results with the robots one. This is a problem when you have parallel works happening at the same time. But we intend to apply all of this in the final task, to apply in our work scenario, real case scenario in Austria. And then the main objective is to, before you start implementation these robots, is we need to analyze the risks that is involved and also to start to measure the mitigations that you could use during this implementation. So thank you very much for your attention.
Thank you, Mauricio. You managed to fit 22 slides in 9 minutes, which is kind of unbelievable. So, yeah, you could have 6 minutes more. So, thank you for giving us this brief introduction on the project. I'll probably have a couple of questions for you later. The next presenter will be Adriana Santos. That's me. Oh, you changed a little bit, but it's okay. So we have Professor Freitas to speak on behalf of Adriana. That will talk about the cost action 354.
Okay, thank you. I'll present Adriana. Adriana is my PhD student, and at the same time, she works for Ascendi for many, many years. She's now finishing her PhD. That's one of the reasons why she's not here, because she needs to finish the works that she started a long time ago. And this, of course, the PhD is done under my coordination, and also Professor Susana Faria, that comes from the Department of Mathematics. And the issue here is, we try to answer to the question if the friction performance indicator defined by the action cost 354 fit the network data. We already heard a lot about friction and why it is so important to model friction, namely in a motorway context where the speeds are quite high. Friction is one of the parameters that are essential for management and is adopted as one of the most relevant for this activity. That's why we need to measure friction and then to predict with time friction. And there are several factors that contribute to the degradation of a pavement. I won't be extensive. And these factors are, of course, traffic, light and heavy traffic. We also have the climate conditions, temperature, precipitation, and relative humidity, which are the ones that we addressed. Geometrical features, plan, profile, and landforms, and also type of surface, among other factors, but these were the ones that we focused and that were available in a network context and in a database. Friction, we needed to assess it as quantitatively. We need it for the present, while models we need it for the future, and we need them to be able to prepare our management activities with time and allocate money to the interventions that are necessary to do a long time. So that's the reason for developing models. In this, there are two aims. One is to develop the longitudinal models to describe the degradation of friction performance indicator over time and identify the factors that influence that behavior among the list that I already presented. The methodology, of course, we must rely on a database, so the data was collected on different roads of the Ascendi network, and this was mostly in the north of Portugal, but anyway, nearly to the middle of Portugal, and here we can capture the effect of the many variables regarding the location and the temperature, humidity, and of course the traffic varies along this section. So it's a quite interesting sample where we can get different effects on friction, even though we are not as the same size as in the United States, so it's the north of Portugal, but the results, I can advance now that they are quite similar. So we worked with sections with 100 meters. Why 100 meters? Because it's a length that is adopted by the motorways as a reference, okay? And we have a total of more than 7,000 sections included in the database. Also, a period of 8 years that was considered. We considered 3 times, so time 0, with the moment where the pavement was constructed, and then 4 years later, and then after 8 years. So 0, 4, and 8. And why this period? Because it is related with what is demanded to the motorway to measure friction and other parameters such as the RI or the texture. Okay? So there's no data available between these periods. And in this methodology, and what we are going to present here was the approach that was done by using the friction performance indicator established in the cost action 354. And this cost action, the objective was the definition of a uniform European performance indicator and indexes for pavements, okay, taking the needs for road users and road operators into account. And the idea was to see if actually these indicators fitted and were good to describe friction and to predict friction with time. In this work, other approaches were done, but in this presentation, the focus is this one. So there are several transfer functions. In this case, the friction is measured with the grip tester, so we selected the proper one, which is this one for devices running at 50 kilometers hour, okay? And the corresponding transformation function. Here are the levels, so 0 corresponds to very good performance, and 5 corresponds to very poor performance. And these are the limits. What happened in this case regarding the National Road Administration, and what is established by this National Road Administration, is that the minimum friction standard value when the road is constructed is 0.6, and then during the life it must comply with a minimum of 0.35. When we look at this, what happens, it actually doesn't fit very well. The limits, what is understood with is very good or bad, doesn't fit with the definition, what is said by the National Portuguese Road Administration, and what was done was to set this limit here as offset point, and what was done was to actually offset the model that was provided by the cost action. And why doesn't fit? Because when you look at this in time 2, which corresponds to 8 years after construction, many sections would be classified as very bad, and actually it doesn't happen in the concession. So what was done was to shift that value to correspond to the classification of the Portuguese way of understanding the levels of friction. So we shift this, and in this case, it fits better what is the classification for what is bad, average, and good. Okay, so we shift that, and then the next step was to model friction. The factors that were considered were traffic, climate conditions, geometric characteristics of the highways, vertical and horizontal alignments, lane and landform, and the type of surface course. So, very briefly, these are some of the factors that were studied. We have a much bigger list, which is not very interesting to show here. We only pass through some of the factors, and among them those that will be statistically correlated with friction. So traffic, of course, it's mandatory to have the traffic. In this case, accumulate annual daily traffic. Climate conditions, we studied a set of a huge set, and we selected these ones: higher value of maximum temperature, average number of days with maximum temperature above 25 degrees, and we also looked at relative humidity. These factors were actually picked up from our National Meteorology Institute, so they are available to everybody, and it was one of the reasons to use them. So it's quite easy to have access to this data. And then for geometric characteristics, the lane, left, right, and slow lane, lanes, straight alignment, clutoid, and circular curve, then slope and the type of the concordance curve, then landform, low altitude, and medium altitude and high altitude, which are the references. And the pavements that are in this motorway network are porous asphalt, gap-graded asphalt concrete, surface coarse, gap-graded asphalt concrete with bitumen modified with high percentage of rubber modified bitumen binder. And what were the models that were selected for this study? And as age is one temporal variable, so we used linear mixed effect models with 2 levels, where level 2 represents the road sections and level 1 represents the repeated measures made on each road section over time. And we also have 2 types of linear mix models with one random effect on the intercept, and I will show what this means, and second random effects, one on the intercept and the other one on the slope of the time variable. Okay, it's better like this. And what does it mean when we have a random intercept? Instead of having only one straight line, we have several lines that fit our data according to the variability that we have. And for example, because time introduces differences, the slope with time can be different from 0 to time or after 4 years, and then from the 4th year to the 8th year. So we also introduced in the model the possibility to have different slopes. And we looked at these with different objectives and perspectives. So here the null model is a mathematical issue that we must pass. So if it is not statistically significant, it means that we can't use the mixed effects model, so we pass that phase. What is interesting for the ones that need this information are these 2 models. The first one that we call the Model 2 considers only the variables inherent to traffic and climatic conditions, which are those that all concessions must have, so the traffic counts, and then the climate conditions, because you can get them from the National Institute that provides them freely. And the second one introduces factors that are intrinsic to highway characteristics, so the geometric parameters that not only all concessions, in the case of Portugal, or road managers have. So what is the idea with Model 2 is to predict the degradation of friction performance indicators through time when there are no data for the geometric characteristics. Okay, so here I won't show a table with all the significant variables because it's a lot of figures. Here are the models that were prepared. So we have here time, traffic, the temperature, the number of days that I explained, okay, relative humidity, and then these parameters that are intrinsic to the model, and I explain all the variability. So in easy ways to understand. Model 2, we introduced lane, plan, profile, surface layer, and landform. And also for those that have this information, we introduced texture. Okay, explained. Okay, then these are the mathematical questions that we have to respect and we have to pass through when we do some modeling. I'll go through this. Okay, and we also did some work comparing the models with one random effect and two random effects, because with one random effects it's easier to run than with two random effects. The model are more simple, and what we got is that when we have two random effects, which means the effect of the time, the models are better. Model number 1, model number 2, and model number 3. So it worth is to use a more complex model. So here we arrive to the fitting of the models that were developed. This is not magnificent. The other models where we didn't consider the cost performance indicator, only friction measured by the grip tester were a little bit better. But anyway, given this R square, it is a quite good model and we can use it for management purposes. Okay, so to finish, so this coefficient of determination suggests a good goodness of fit between observed and fit values, and it confirmed that traffic has an effect, and of course the higher the traffic, then the lower the friction, or in this case is the opposite, because level 0 is the good one and level 5 is the bad one. So we have to look at this with the opposite signs of the friction. We had the effect of the climate conditions also, namely temperature, so the position of the pavements is important. We have the effect of texture, which is exactly the same. The higher the texture, the higher the friction. Effect of the characteristics of the highway, which means, and it goes with what Gerardo showed, we must pay attention to the area, because in that areas the friction is actually lower. There's also a difference in the surface course, so it doesn't behave in the same way for the different surface courses, and we must pay attention to that. So all factors affect the friction and affect the performance indicator that was used to study this. So to conclude, we used the linear mixed effects models successfully to describe the degradation of friction parameter, and we identified these factors that I will not repeat. and that are clear in line what we saw in the keynote presentation. Also, these models fit the needs of road managers, and they are quite simple. And when there's data that is more complex, we have benefits in using a more complex model, introducing, for example, the texture. So thank you very much.
Thank you very much, Elisabetta, for presenting us this work by you and Adriana. So also take my regards to Adriana. As we clearly understood, when it comes to friction, you really need a lot of data and from different sources, and then you need to put them together. And so you also need a lot of mathematics and statistics. So it's quite a tough task. But we see our colleagues are managing, and I also think that our next presenter, João Afonso, is not exactly dealing with friction, but is dealing with asphalt surface rejuvenator. So Afonso, the floor is yours.
Good morning, everyone. I'm here to make a presentation about a surface treatment technique that is taking its first steps here in Portugal. And as I came from the contractor and the concessionaire side, this will be a very practical presentation. I'll start with a brief framework of the subconcessions where we undertake this test trial. I'll go further to an introduction on how the team appeared among us. Then I'll tell something about the activities of the test trial. After, I'll go deeper on the monitoring campaign we undertook to determine the surface characteristics, and I'll end up with the usual conclusions and further developments. Now, a brief framework about the subconcession. It was awarded in 2008, and it was open to traffic between the end of 2010 and mid-2012. It comprises 242 kilometers of routes divided between two main axles, the EC5 that links the A4 motorway with almost the border between Portugal and Spain, and the EP2 between another junction with the A4 and the junction with the A25 highway. And nowadays, the management and operation is being carried out by Subconcessionária do Douro Interior. And just a brief photograph of the operation and maintenance center. And as I say many times, it is a pleasure to be able to work with pavements with this type of landscapes. Now, in 2021, pavements were already showing some signs of aging. We can see the pavement surface as that grayish color that indicates aging. We knew that there were no structural issues following the FWD campaigns. We knew that the pavement had enough bearing capacity to face future traffic projections. So it was decided to undertake the rehabilitation of the surface layer. The pavement rehabilitations. On the areas with the most severe distresses, it was decided to mill the surface layer with 5 centimeters and replace it with an asphalt concrete produced with modified bitumen. I would like to draw to attention that we are in an area with a high thermal amplitude. We can reach more than 40 degrees during summer and sub-zero temperatures during the winter. And on the remaining area of the existing surface layer, we will be applying a rejuvenating emulsion. About the asphalt surface rejuvenator, the rejuvenating emulsion. There was experience in other countries, but at the date, it was practically non-existent in Portugal. We knew another concessionaire had some experience, but in another type of surface layers. So there was the need to define the best construction method. And we had serious doubts regarding the potential effect on the pavement surface characteristics. After all, we will be spreading a bituminous emulsion on the surface of the pavement. To solve all these points, there is nothing like making a site test trial. The site test trial was performed on the junction, on the interchange between EC5 and EP2 on the ramp. We chose the D ramp because we had 750 meters available to do the test trial. And we divided the available distance in 5 substretches. The first substretches, we called it the reference stretches, and we did no application of the rejuvenator. The next 300 meters, we applied a type of rejuvenator called Neomax Echo at 2 different taxes. And on the last 300 meters, we applied another type of rejuvenating emulsion. The execution of the test trial. On the day before, we washed the pavement with water because we wanted to ensure the most uniform conditions possible in the test trial, and on an attempt also to increase the efficiency of the application of the rejuvenator. On the test trial, we started by applying the emulsion using traditional equipment. The emulsion was applied at a temperature of 60 degrees, and the equipment was going at 5 kilometers per hour. Right after the application of the emulsions, we spread some gritting sand, a 0,2 sand, at an application rate of 200 grams per square meter, because we wanted to provide good initial grip conditions. At least not so bad. And 30 minutes after the gritting sand has been spread, the jungle was open to traffic. Now, to monitor the surface characteristics, we thought putting into practice this campaign. We will be defining the control point 0, that is the measurement after the pavement has been washed and before the application of the rejuvenating emulsions. And then, immediately after the application, 24 hours after the application, 1 week, 1 month, 3 months, and 6 months after the opening to traffic, we will be again monitoring the surface characteristics to be able to take our own conclusions. Very important. We didn't want to dirt or oils to influence our results. So before every campaign, we washed the pavement. About the grip measurements, we did a continuous measurement with grip testers with verifications by precious pendulum. Nowadays, some of us don't recall, but there was a time where even to perform site tests, we had to wear masks. An important note, during the first week, it was impossible to make grip measurements with grip tester and with the British pendulum because the emulsion didn't have enough cure conditions. And this is the results of the grip measurements. The first and probably most important conclusions is that at no time we went below the minimum operation level defined by the quality control manual. Going further into the analysis, we were expecting that on the reference stretch, on the first 150 meters, the grip levels to be almost the same, but they are quite different. And we noticed that on the colder months, the grip levels were higher than on the hotter months. So we needed to cater for temperature corrections. The correction we performed was a translation of the curves so that on the reference stretch, the average grip number was the same. And these are the results. And now we can clearly see that right after the application of the rejuvenator, we have a decrease on the grip levels, but at no point below the 0.35 minimum level, and During the next 6 months, the grip level recovers as expected and becomes almost the same as before the application of the rejuvenator. About the microtexture measurements, we also did continuous measurements with discrete verification by the sand patch method. These are the results. We didn't see any significant variations between all the measurements we made. Again, at no point we went below the minimum operational level. We did the same exercise, trying to correct for temperature, and we didn't draw any conclusions from this. We know that it appears to be a slightly decrease in the macro texture. The final conclusions. The method statement for the rejuvenator application was validated. It was verified the effect of the rejuvenator over the pavement surface characteristics. We made some contributions for a correct definition and interpretation of test trials prepared for monitoring grip levels evolution. It is very important to clean the test trial so that dirt and oil don't influence the results, and also to correct for the temperature. And the data retrieved by the concessionaire will make us be able to make decisions about pavement maintenance based on real data and complete and reliable information. Further developments. Now we are monitoring the raveling. We applied a surface rejuvenator, so we don't want the pavement to ravel, and we will be monitoring this during the next years. And on an attempt to develop lab tests that can demonstrate the efficiency of the rejuvenator application, we adapted an European standard. We have an European standard that intends to determine the resistance to fuel, where we place the samples on fuel and then we brush them and we determine the loss of aggregate. Obviously, we didn't place the samples on fuel, but we brushed the samples before the application of the rejuvenator and after the application of the rejuvenator. We are still performing these tests because we want to do them at different time stages. We already have some conclusions, is that macro texture and air voids may influence the efficiency of the rejuvenator. This is ongoing work with LNEC, the National Laboratory. Thank you very much.
Thank you very much, Afonso, for your presentation on this technique. And I think it's time now for questions. We are running slightly late, but I think if Professor Pereira is happy with it, we'll go on with some questions. I do have many, but I'll first leave floor to the audience. If there's anyone that has a question, please raise your hand. Don't be shy. I know you're still suffering from wine. Well, just to ice break, I'll start. I'm very curious on Afonso's work, and I was interested in understanding the type of material it's applied. Is this a standard emulsion with some grit sand on it? Okay, so let's say it's emulsion plus an additive inside. Okay, very interesting topic. As for the temperature alignment, I think on the grip number test, you might want to talk to Professor David Woodward here in the audience. He might give you some hints on how to make the translations, right? I mean, the method you use, I think, is pretty much clever. I do have a first question for Gerardo, if there's no question from the audience. And my question is, we are looking at one side of the coin, because the pavement, like we work on pavement, and we are working on that side of the coin. But if we look at the other side of the coin, it's tires. So my question is there any management of tires in US? I mean, in Italy, for instance, you are supposed to have a certain thickness of your thread. They don't check the pressure of the tire quite often. I mean, you don't get fined if the pressure, you should, but I never heard someone getting a fine on it. I know in US you have WIM systems, VIM systems running on the motorways, and I'm seeing pictures with many stars of WIMs. Do you get a fine if the pressure of your tire is not right?
No, that's a good question, and no, the only control is a part of the safety inspection. Every year they check the amount of thread that remaining, and there's a minimum for that. And if you have it any part of the tire, you go below that minimum, you have to replace your tire. You don't pass an inspection. But no, we don't control the tire, and it's an important factor too. And it's also part of the equation, because depending on what tires you use, you get more friction or less friction too. But that's a variable we cannot control as highway engineers, but it's important. And again, it go back to that concept of safe system. It's just not just a safe road. You have a safe vehicle, you have a safe driver, you have all the stuff to minimize crashes.
Yeah, thank you. That what I thought, that it should be done something also on the other side of the coin, because if we manage to save lives, reducing 30% crashes with this change in friction, then we might also save an additional amount of lives if we manage to control the pressure and the characteristic of the tires. I know the 20 cents trick in the UK. They just check with one of the coins they have. Don't think that the coin is still around in the UK, but no questions so far. So I'll do a last one, maybe to Mauricio. I was pretty much curious to understand which kind of robots you're talking about in the working side, because it looks like we are quite far from having robots working on our roads, although we know some research is actually going on the use of robots for crack sealing. So can you please come forward and tell us something about the robots you're thinking or in your vision about road maintenance?
Thank you for the question. So there are two types of robots. The first type is totally autonomous. That's, for example, for painting. So based on GPS and other information, it can paint the road. So this is the first type. And also for pothole filling. So you have a machine that goes to the pothole, it do like a 3D scanning, and then it do a 3D printing. It's more like an asphalt emulsion that you put, and then the the cars will compact the asphalt. And the second kind is for the big machines that are not totally autonomous. You have enhancements in the process. It's like when you have the cars at the levels of cars autonomy. So now we are dealing with add more information, for example, GPS or scanning the road. So the driver of the paver, it can be more confident, let's say, during the process. So you have these two kinds of robots. One that's totally autonomous, and the second one is not a robot, but is a more enhancement of the process.
Okay, thank you. You may want to have a look at what George Chang from Transtech, I guess some guests from US know him, on intelligent construction systems. There's a nice website on this using their tools. It's actually almost an association, I believe. So you want to have a look at this and see what they are proposing as new technologies for robotizing the construction. Okay, indeed. Yeah, we do have a question here from the audience.
Is to Gerardo about, because in Europe we have a labeling for tires, a labeling based on rolling resistance, friction, and noise. And what do you think about your system, considering a labeling also for the road? That could be the other side of the coin.
Yeah, that's it's interesting because I had one slide about this balance, and I took it out because the presentation was too long already. But yeah, there's a compromise, because if we increase friction, we will probably increase noise and also rolling resistance. So we are trying to find a good balance between that, and some surfaces may have maybe improvement in all three areas, but I guess that's something we haven't looked at. Truly, our level of microtexture in the US is considerably lower than the one here in Europe. So that's a little bit less of a balance there, because we're still in I would consider a very low value. Some states, they have microtextures of 0.3, 0.4 millimeters that for high-speed highways, we don't believe those are okay. But the mix has a lot of durability, and that's another factor that plays. Is maybe not related with the surface properties, but it is related with the structural deterioration of the mixes. One of our neighbors, we've been looking at their mixes because they last longer than the ones in Virginia, and what we found is they're also less safe. So it's a compromise again, and eventually somebody has to make a decision how much is good. But what's happened in the US the last few years, we put a lot of emphasis on reducing crashes, because surprisingly, crashes were going down, but they start to go up, and they're higher now than they were before the pandemic for some reason. I have my opinion. Maybe it's something to do with distraction and cell phones and things like that. But truly, I don't have a good proof of that. There's some of the folks that they work at the institute that deal with human factors. That's what they think probably has something to do with it. So yes, we have to balance. We have to find the sweet spot there, where we have a mix that has appropriate safety, appropriate energy consumption in terms of rolling resistance, and low noise. Noise is something we have not put a lot of emphasis in the US. We have so far one project that was mandated by the legislation on look at low noise payments. We have some good solutions with the open porous asphalt rubber mixes, but fortunately they did not maintain them. So 3 years after we placed them, the noise benefit was mostly gone after that. But it is a good point. But the durability versus safety issue is something that's the main focus right now. And again, trying to incorporate the safety as part of the mixed design process. That's the next step. How much microtexture we want to ask for, that's a different question. I don't have an answer, but this is something we're discussing.
Okay, thank you, Gerardo. And I think that there's no more time for this session, and I please welcome all the presenters again and thank them with a nice applause. Yeah, I invite you for the break outside, and there will be next session. I think it was scheduled 10:30, but I think there's 20 minutes delay. So see you in a while.
Paulo, estás bom?
Estás bom? Posso meter aí a minha apresentação?
Podes. Deixa-me só colocar a minha.
Hã?
Deixa-me só colocar a minha.
Tens agora uma apresentação?
Não, é de um aluno meu. Pá. O gajo está em Timor.
Podias
Então,
fazer também a minha, pá.
pá, ontem fiz uma também.
Um instantinho.
Uns gajos que do Boteco de Bragança que não podiam. Então eu fiz a apresentação por eles. Deixa lá. Eu não combinei nada contigo porque eu vou te ficar aqui.
Eu também. Sim, eu não vi o teu nome, não sabia se estavas, mas também vou ter de ir para Vila Real a seguir. Bom dia.
Olá.
Está?
O computador, tudo a funcionar.
Tem? Isto é assim, não é? Oh, perfeito. Já está a dar.
Não sei. Para teres.
Agora deixa-me ver se me lembro como é que nos Windows isto faz. Onde é que. Está aqui, não é? Aqui. Ejetar. Se ejeta a pen, tiram, não é?
Sim, tira. Nomear isto aqui. Portanto, o teu é o primeiro. F2. O teu é o primeiro. E esta aqui é a última. F2.
Substituir.
E esta é a 5. Olha. Sim, tipo à frente. É uma coisa esquisita. Não sei como é que eles conseguem controlar. Não tem espaço para uma petita. Sim, não, mas repara.
O Alfa Romeo também não tem.
Sim, mas aquele lado, à frente tem radares, mesmo no centro tem radares. E depois, o meu também tem radares. Chata, não fica só por baixo.
Os gajos cumprem o facto de que são cargos daqui.
Se puser um pouco mais, vai ter assim.
Olha, vou dizer hoje não tinha.
already marked the tires so they can follow. Yeah, in that case, we're looking into getting the actually, we get we get very accurate testing with the content. We get areas and no, but that's interesting because that was Ricardo's idea. I have the old age factor, so it's except for California. Yeah,
And it's nice because I work with a math teacher. Where is that?
The first
Here.
one. No.
That one? Okay. And I put this out.
Wherever. Okay, so this is. Yeah, okay.
I'm lost. Is for that session what you want to show, or
Yeah,
for
this
the?
is it. For,
Okay. So I'll put it outside.
thanks. No. And it's with audio, so audio is connected, right?
Yes.
Okay, that's good.
Força, força. Ai.
You can turn it off somewhere.
No, it's upstairs. So next time, Daft.
That's the plan.
Okay.
We have it here.
Okay. It's here.
Yeah, do a quick click if it turns, okay?
Okay. Welcome.
Welcome back. Okay, welcome back. We are getting ready to start with the last session of this great conference. I think people are getting in, but should we start or wait? Start? Okay. So it's my pleasure to introduce the last invited speaker for the conference, Professor Alicia Pinto. Is an associate professor with habilitation in economics at the University of Minnesota, with a PhD in economics from the University of South Carolina in the US. Her research interests focus on applied macroeconomics, in particular the application of experimental and behavior economics into the areas of environmental and health, contemporary economic policy, games and economic behavior. That's the journals. It's been published among other ones, and the International Journal of Life Cycle Assessment. So please join us with your presentation. You should be able to find it.
Okay, thank you very much for the invitation to be here today. I'm presenting a paper, a joint paper with Paulo Ramísio and Diogo Aredes, and the paper, the origin of the paper was to try to mix two different scientific areas, engineering and economics. So my colleagues are from the engineering side, and I am from the economics side. The basic idea was to see, so highway runoff pollution is a known fact in engineering, and it is also a known fact that solutions need money to be implemented, and so the economic side came into the question here. So the co-financing model for the mitigation of highway runoff pollution was the title that we came up for this paper. It has been published in the Journal of Environmental Management. And so the basic idea is then, so we have rural and highway runoff pollution, which generates what we call externalities, and in engineering it's also externalities. So undesirable effects from one desirable action, which is going from one place to the other. These externalities is known to be causing water bodies and ecosystem damages, which then eventually affect quality of life of humans. So the two big questions: are there technical solutions that are available to reduce these externalities and the damages associated with them? And then who should pay for the implementation of these technologies or technical solutions? So I'm going to go very quickly over the engineering part, which obviously is not my thing, and then I'll go slower on the economics part. So main pollutants and build-up conditions for runoff pollution. So highway runoff is a linear source of diffuse pollution with considerable pollution load associated to acute and chronic effects on the environment, ecosystem, and human health. Type of pollutants and severity of its effects depends on several factors, and these are just some of the factors that affect the severity and the presence of the pollutions. It's also related with mobile and stationary sources that include then these other sources, so combustion of fuel, oils and fuel leakages, wear of the vehicle components, dumping of substances, and so on. The pollution, how has it been computed in the past? So we have regression equation, which basically gather information from several sites, events, and then try to estimate the quantity and the quality of runoff pollution associated with the use of the road. There are statistical techniques who try to estimate runoff event mean concentration and loads associated and the associated probability of occurrence of these pollution events, and also simulation models which are deterministic representation of watershed and associated phenomenon to predict then urban and highway runoff quality. So here we present some of these simulation models that have been used in the literature, and I won't go into details into these ones. So basically, since pollutants concentration vary within and intra events and also among sites, usually the two measures that are computed is event mean concentration or site mean concentration of each of the pollutant that is relevant. So there are several techniques to address the problem, and these techniques have also evolved over time in designation and names. We are using the one that best fits our approach is the best management practices that we are then using here. So 6 stormwater management pollution practices were considered. So dry basins, wet basins, sand filters, bioretention filters, constructed wetlands, and infiltration trench. Those can be designated as nature-based solutions or close to nature-based solutions. And here we present some technical data on each of these solutions that we got from previous research. So we have median retention efficiency per pollutant per solution, and then the annual cost range of these solutions as well. Now, going to the economics and regulatory side. So runway or runoff pollution have one characteristic that is it is a diffuse source of pollution, and from this good action that is already an intended action from going to one place to the other, so mobility, it results this externality, unwanted externality. So in economics, we divide this type of goods, let's say, we try to characterize them in 2 dimensions, excludability and rivalry. So excludability measures how easy it is to exclude the user from using the resource by some mechanism, most of the times price. Rivalry means how the use of the resource is rival between users. So how much when one user uses the resource, how much it affects the quantity or the quality of the resource to be used by other users. So in giving these 2 dimensions, we have private goods, high excludability, high rivalry in consumption. We have pure public goods, which is low excludability, low rivalry in consumption. And then we have 2 other intermediate, let's say, type of goods. It used to be the case that we have many pure public goods, like air, water quality, and landscape, and so many other pure public goods, which, given the type of use that humanity has been doing in the past, are no longer pure public goods, but they transform into what we call common goods, which are similar except that they have a higher degree of rivalry in consumption. So it is no longer the case that the damage done to water bodies, for example, does not affect the quality of the water body because it's too much for the water body to recuperate from the damage. So instead of having pure public goods, in most of the cases now we have common goods. Still we have pure public goods like, for example, national defense, okay, public lighting, those are pure public goods. So with common goods having some degree of rivalry, then obviously we need some policy to control for the damage, for the overuse of these resources, which tend to happen. And if we have some excludability, then we are in a better solution than when we do not have this excludability as a possibility. So to apply the polluter pays principle, we need to have some excludability. We need to identify the polluter and go after him and be able to charge for the damage that he's producing. With diffuse sources of pollution, it's more difficult to do this approach. When there is also some degree of scarcity, then we have more rivalry and so more damage. So in a sense, what we have in runoff pollution is, in some cases, we might have some excludability conditions like highways, which have a toll system. So it's possible to prevent the user from entering without paying. National roads, it's different. This excludability is not present because everyone can enter and there is no system to stop entering without payment. So in terms of economic regulation or regulation of this type of externalities, so economic regulation of externalities, what it wants to do is to correct the signals for the use of the resource. Being from economics, one of the signals that is best used is price. Okay? We want to correct the price that the user is paying for some resource for these other consequences that are not accountable, are not accounted in the price yet. Selecting the best regulatory instrument requires previous and rigorous assessment of the characteristics of the situation under study, because there is not one best solution for all the problems within regulatory economics. So particularly important is the analysis of how much information is available to the regulator, the quality of the information that the regulator has, and the structure of the incentives for each of the stakeholder that is involved in the problem. So information is a first issue that needs to be addressed. What is the type of information that is available? What's the quality of that information that is available? And then understand the incentives of the stakeholders involved. So what are the determinants of the behavior of each agent using the resource, so that then we can manipulate these determinants in order to deviate from the bad behavior to the good behavior. So the reality is that stormwater was absent from legislation, from regulation, although in some cases stormwater contaminant levels are higher than the limit levels for urban drainage. Right now, so at the present in Portugal, it is not yet totally included in the regulation, although this strategic plan, PENSAR 2030, already includes 1 or 2 lines for stormwater pollution, but is very, very shy, I would say, in addressing the problem. The EU proposal directive on wastewater treatment also now includes some lines regarding stormwater, but again, it is still a proposal, and again, it is a very shy address of the problem, which tends to be, this problem tends to be increasing in importance. So there is this legal vacuum in Europe regarding stormwater management, and the responsibilities are then not attributed to any specific agent, so there is this problem of implementing any solution. So this is the question that led us to start working. So there is technical knowledge, there are technical solutions to address the problem. We need to think what is the most attractive solution for each case, given the characteristics of the road. Nevertheless, the implementation of these solutions, of all solutions, requires some level of investment. And so the question is, who should pay for this investment? Is it concessionaries of the highways? It is the state? Should it be the users? What's the best, in terms of incentives, who can best prevent the damage that occurs from runoff pollution? And that's the person who should be paying, is the one that can best prevent the damage from occurring, which is easier than to have the problem solved. So we thought about a co-financing model. So urban stormwater are open systems, and such control of this externality is complex. In high runoff, we thought it would be the best first case to be approached, since, as I said before, there is a toll system that prevents users from using the resource without paying, so there is a payment mechanism already implemented, so it would be a question of adding a layer to this payment mechanism to pay for the management of the externalities. Okay, so the main challenge then is to compute a price or a value for these externalities that are generated by using the highway. So despite the possibility to charge users for the externalities caused by highway traffic, there is no experience of the kind in Europe that we know of. So our proposal is to analyze the elements that constitute a possible new regulation on highway runoff, focusing on highway tolled sections with the aim of promoting the internalization of the cost of the externalities for the users. Okay, so evaluating then the externality. We are going to evaluate the cost of alternative mitigation measures and also the benefit caused by control of this externality. Regarding the benefits, in economics, we have two families of valuation methods. So indirect valuation methods, also called revealed preferences, observe the behavior of the agent and from the behavior try to infer the value that they attribute to an externality. So a very simple example, if you think about a biological variety of milk and a non-biological variety of milk, so a certified biological milk and a non-biological milk. If we see someone buying the biological one, which causes 10 cents more, then we know that this person at least values the biological variety by 10 cents. Okay? If we see someone looking at two packages and does not buy the biological, what we can infer is that for this person, the biological variety does not worth 10 cents more of the price. So these are revealed preferences. The other family of methods is direct valuation methods or stated preferences. And for this, we don't observe behavior and try to infer the preferences. These are methods that are based on surveys, and we ask people in a certain way how much they are willing to pay for, going into our example, the biological variety of milk. So it's stated, they state their preferences, and they not reveal the preferences. So contingent valuation method is one of the methods that rely on stated preferences, and basically it computes the income that a citizen is willing to forego to get, to prevent a specific environmental damage or to get a specific environmental benefit. I'm saying environmental, but it can be of other natures. So basically, we assume that citizens, agents have what we call a utility function. It's like utility. The word is self-explanatory, and this utility depends on, let's see, on the quantity of, so a set of goods that this consumer buys, and this is like a deterministic part, and also it also has a random component. So we have a deterministic component depending on the goods that this person chooses, and then a random component which is not deterministic. So what we see, what we expect is for someone to choose alternative I over alternative J if the utility that he derives from I is greater than the utility he derives from J. And given that there is this random component and the utility is not observable, is something that people enjoy. So what we have is the probability of choosing one alternative given the set of goods that are available is the probability that the utility of I is greater than the utility from the choice J. Okay, this is what we model as for consumer choice behavior. So, using that framework, now going into our case study. So we used Highway A1, which is the biggest highway in Portugal, goes from Porto to Lisbon. It has about 230 kilometers long. It is composed of 25 tolled sectors, and we predict the stormwater total costs from the period 2019 to 2039. We estimate the willingness to pay for implementing this solution, and here are some information. So 279 kilometers, I was wrong at the first, A1. So it's more than 50% of the country's length, and it includes several stations for measuring pollution levels. So these are the toll stations in the bottom of the graph. So here are all the toll sections in the highway, and we have total number of passages and total costs associated with the toll system. We control for annual precipitation and variation of this precipitation monthly. So we can see that we have significant monthly variation of precipitation, and also annually variation of precipitation is also significant. Here are these 6 rain gauge stations. So they are ordered by precipitation, and you can see significant variability over precipitation over these control stations. So considering the work of Weiss et al. 2007, Claytor and Schuller 96, and the G-Terra project from Portugal, we were able to estimate future pollution loads. And here are the results from this estimation, and I'll go very quickly. This is a 20-year prediction of pollution load analysis in tons. And here are the costs that were estimated based on previous literature for two settings with more or less amplitudes of the implementation of the solution. So the size of the solution was different between max and min. So this is the total present cost estimated per solution. So we have, depending on the water quality volume, so the 2 scenarios on water quality volume, as I was saying. So costs are different between the 6 solutions, and they vary also with the size of the solution being implemented. So these are the cost data that we used for each solution, or the cost range, I should say, for each technology implemented. Now, regarding the benefit calculation, so we did a survey, more than 1,000 respondents to this survey. And although we asked before if people were aware of stormwater pollution, if they knew what stormwater pollution was, before asking the valuation question, we provided some information, and this was the information that was provided. And the idea is that we may have people with very different knowledge levels when answering the valuation question. What this information intends to do is to get some common base of knowledge so that they can answer the evaluation question. So it reads, roads due to traffic present high levels of pollution in pavements, particularly when there is precipitation, stormwater washes pavements and takes pollutants to surrounding areas. This phenomenon is known as road runoff. The contamination caused by road runoff generates significant financial, social, and environmental costs and substantial impacts on health and quality of life of population. The implementation of road runoff treatment system mitigates the negative effects of street runoff and diminishes their associated impact. So, common language that explains a little bit what is the problem and the origin of the problem, but also that there is solutions to this problem. So the evaluation question were, do you agree that citizens should participate in the process of installing street runoff treatment system? Yes or no? Taking into account your income and regular expenses, what is the maximum amount that you would be willing to pay additionally to the current toll? And it goes from 1% until more than 20%. Now, this valuation question is a typical contingent valuation question. It has one particular element that is included in here, which is this part saying, taking into account your income and your regular expenses. Now, going to behavioral economics, we should not expect that reminding people of their income and their expenses would make any difference in the answer, because they know we are not providing any information, right? We are just saying, remind yourself how much you earn and where do you spend your money, and now answer this question. What it has been shown is that when not introduced this reminder, people tend to overstate their willingness to pay, since this is hypothetical, so they are not paying. Is how much would you be willing to if you were present in this situation? And so it has been shown that usually people overstate how much they are willing to pay, but having controlled, having done several experiments on the issue with known private goods with a known price, what has been found is that reminding people of how much they earn, how much they spend usually, it decreased significantly this hypothetical overstatement of how much people are willing to pay, and actually people reveal values that are very close to their true valuation of that particular resource, in the case, this externality that we are trying to value. So here are some graphs. So the first graph there is the mode of transportation. So we have bicycle, car, bus, train, and walk. We can see that about 50% of our respondents use car for their regular travels. Then do they use highways? So on the bottom we have daily, occasionally, 1 to 3 times per week, never. So occasionally has about 55% of the answers, and then 1 to 3 times a week, about 20-something%. So we have about, we have a regular use of highway. Then how many kilometers do they travel per week? So it's this graph here. So the most frequent is 35, something like that. So 35% travel less than 50 kilometers per week. About 30 travel between 50 and 200. So we have significant use of highway. So our sample is composed of people who use highways with some regular frequency and use it somewhat intensively. Are you aware of what is street runoff? So yes is this one, so it's about 35%. No is 1 minus this. So this is one of the controls for understanding whether that information was relevant. And yes, obviously it was relevant. Are you aware of the impact that runoff pollution has on the quality of life? So from a scale from 1 to 6, we have 4 and 5 as the most frequent. Are you aware of the impact on the environment? We have a higher percentage being aware of the impact on the environment, and the impact on water is not so much. So people were more aware of the impact on the environment than on the impact of their quality of life and quality of water. Do you agree that the system should be implemented to prevent the damages? Overwhelmingly, yes. Should users pay 50-50? 50 say yes, 50 say no. Of those that are willing, that agree that users should pay, how much would they be willing to pay? On average, it's this graph. So as expected, this is a decreasing line. It should be a decreasing line. If we had that hypothetical nature of the question, then we should expect a bump here, so a higher percentage there, which we don't observe, which is a good sign for the quality of the data. And we'll see a little bit more. So we estimated a two-part model, so assuming that our respondents first think whether they are willing to pay or not a higher toll for implementing a system to control stormwater pollution, and if yes, if they decide yes, I should pay, then how much I should pay. So the first column here is a probit model, and it explains the decision to yes or no, am I willing to pay or not? Then the second column is how much should I pay? And the third is the combined effect of both of the models. So what do we have here? We have that, so the sample is 1,192 subjects, of which 679 are willing to pay something, and then we have again the total sample. So we have good quality information here. So we always have in this, when we applied contingent valuation method to judge whether the data that we got is of high or low quality, we look for from what we call, it's time for me to, okay, it's 5 minutes. So we look for, in these regressions, whether we have what we call empirical regularities. That is something that is not the theory that says it should happen, but in repeated applications of the method in the same circumstances, this result tends to happen. So one result that tends to happen is if people use the resource more intensively, then they should be willing to pay lower amounts because it's going to be heavier on their budget. So we have the good result there. So we have a negative sign on the number of kilometers traveled with a negative relationship of how much people are willing to pay. The next variable is, should citizens be liable for paying for control of stormwater pollution? Has a positive effect on how much people are willing to pay. So again, it is consistent, what we would expect from rational agents. Then we have younger respondents, female respondents, being willing to pay on average more than older male respondents. This is again an empirical regularity. Usually women are more pro-environmental, have a more pro-environmental behavior, and younger people tend to be also more pro-environmental behavior. So, and we have this result here. Higher income, higher willingness to pay, again, an empirical regularities, meaning that we are in a good It's a good way for having good quality data. Do they agree with a system that would control for for stormwater pollution? Those that agree with the implementation of the system are also willing to pay a higher amount. So based on this model, predicted willingness to pay is 1.63 percentage points on average. So this is the data, the result that we get from how much people would be willing to pay to finance, co-finance the implementation of stormwater pollution solutions, technologies, if you want. Again, stressing that although I know for engineers is not asking people their opinion is not usually a thing that you trust. Economists don't also trust opinions, but they have methods to judge if we should trust what people are saying, are telling us. And again, these empirical regularities that we observe give us confidence that we should trust the information that people are providing. With the note that this information is context specific, and in this case is sample specific, since we don't have a sample that is representative of the national population, okay? But the methodology is robust. We had a good result, good in the sense that quality, the confidence that we can have on the result is valid. Okay, crossing now cost and valuation. So what we have here in this graph, we have per stormwater management practices. So we have the 6 that we talked before. And here we have the ratio between the cost and how much people are willing to pay. So as costs vary between between practices, here we have the range for those 2 levels, so those 2 scenarios that I mentioned previously, which is the quantity of water that is being addressed. For some solutions, the coverage of the cost can go between 2.1 and 2.6%, so the part that the citizen is willing to pay would be around 2.1 to 2.6% of the total cost of implementing this solution. But for others, the coverage of the cost can go up to 20%, which is not a small percentage of the total investment. Okay, so in sum, we selected 6 of the most prominent stormwater management practices for highway runoff control. We have 2 quality volumes, scenarios that were implemented. We computed expected present costs. And then evaluated the economic sustainability of implementing a co-financing system, contemplating also the social acceptability of the solution. Let me go back, which means this thing here. So this probit, which is the probability that people agree to pay, is what we call the social acceptability of the co-financing system. Okay, so the survey for this number of persons, so the results achieved indicate that depending on the technology that is selected, users are willing to pay between 2.1 and 2.6% in the most expensive technology, but it can go up to 21.8% in the least expensive technology. So what we conclude more broadly about this paper, is that looking at stormwater management practices, that we have the technologies, you have the technologies, they are known, they are established. There is on the other side, there is a very clear increase on the awareness that citizens have regarding the externalities or the costs that they impose by their behavior on the environment, which now is more clear, the link between the damage that we do to environmental goods and the damage to our quality of life, which is now a clearer link than it was before. And the more clear this link between the action of the citizen, the damage to the environment, and how it fires back to the quality of the system, the easier it is to control the behavior of the subject. So if the person, the citizen, is more aware of the consequence of his behavior and how this will hurt him in the future, the easier it is to manipulate his behavior, because he's aware, if I change, this changes in the environment, and so my quality of life increases. So the clearer is the link, the easier it is to do policy to change that behavior. So since we expect that citizens become, and we are seeing that, become more and more aware of this link between behavior and quality of life, then we think that promoting this new paradigm that is more holistic, more comprehensive, in a more articulated, multidisciplinary approach can be one that regulatory authorities or the governments can more easily implement. What this paper shows is that, in fact, it is possible to have citizens participate in highway runoff pollution, which has already a toll system implemented. It's obviously, we are not saying that this is doable for other roads who do not have this toll system implemented, but it can give regulators an idea for first addressing the easiest issue, which is maybe highway, and then we can move on to other solutions that are not so easy to be implemented, but at least a step was put forth into implementing solutions. Having citizens co-financing the solution, which has the advantage of obviously bringing more money into the investment, but it has another, in my opinion as a social scientist, even more important consequence or side effect, which is having citizens aware of the damage that they cause. And that's the link to then change the behavior, if they are aware of the damage. So that's it. Thank you very much for your attention. I don't know if we do questions now. Or?
Will be at the end of the section. So thank you very much, Professor Pinto, and for a very interesting presentation, an approach that we are not used to listen to as civil engineers, but I think important for what we do. So we'll move directly to the other presentations, and then we have a discussion sections at the end. The next presenter is Pablo Ramicio, that will be talking about a hydrologically based model for estimation of road drainage infrastructure resiliency to climate change. You have 15 minutes.
Thank you. Good morning. It will be my great pleasure to present an ongoing project that is seeking a hydrologic-based model to estimate the resilience of urban road drainage infrastructures, especially to address climate change. This project is shared with my colleagues, Fernando Sousa and Clara Vieira. Let's start by hydrology, hydraulics, and hydraulic design. When we look at highway design, it's easy and simple to do this concept model where we should address different processes. First, rainfall, then interception that has different sub-processes, and then fluid routing. And this is quite simple to understand, but when we get to real results and real data, things start to get a little complicated. Why? First, because we have discrete rain gauges. They have different times of operation, different signals, and some were daily, some have hour registration, and we get a lot of data that has to be statistically treated. And another problem is that the precipitation is registered in a point, and we have to transform this precipitation to an area. So that's the first assumption that we have to do. How can we aggregate data that we have from precipitations? As an example, in Portugal, the regulation that is now being addressed is from '95, and it only considers a division of Portugal in 3 zones. So that's a huge assumption and a big simplification. So we have these kinds of maps that give us an idea of the intensity of precipitation that should be used for the design of hydraulic infrastructures. But there's another problem, because when we deal with culverts, most drainage basins are very small and they have a short concentration time. And since most of the data that we have from rainfall is from 1 hour, we have to transform the data that we have based on 1 hour to sub-hour data. And that's another problem that we have to do, and we have to treat it statistically. And we have another problem, is that climate is changing. So we have data from temperature and precipitation, here from 1970 to 2000. In red, we see the average of between the years in Portugal and in the north with a 10 and 90% percentile. So they are changing, we know that from the past, and we don't know how they're going to change in the future. Furthermore, we can see that this is also going to precipitation, and we are talking about average annual precipitation. We also studied monthly precipitation, and it varies highly between months. But it's not this kind of data that is concerning us. It's the short intensities. That's what is most concerning. And when we transform, and there's a big step here, when we transform precipitation into flow, we have different ways of doing this. One is in the right, we can do hydrologic model. It's something that's easy now. We have free open source models, but they are very time consuming and you have to have a lot of data. So it's an important process. It's nice to do, but we do it in big drainage areas. That's not the case of most of the drainage areas that are associated to culverts in highway. So this is one process. The other one is to separate in events. So we analyze an event, we can see that there are a lot of areas in the event, and we start to simplify this. So one way is to consider a linear growth, a linear decrease, and a maximum flow. Well, there's another level of simplification, and that's the level that is mostly done, is to only consider the maximum flow. And you don't know and you don't estimate how many times, what's the time that maximum flow will occur. So let's look at the problem. The problem is that when you design a highway, you have some available data, mostly sometimes it's old data, maybe it's not refined data, but you have to use it. You don't consider the change over time of climate, and you have considered that the soil permits equal with the same occupation through the next decades. So you use simplified flow estimation models. And this is what you do in the design criteria phase. But several years later, you have a huge infrastructure, and you see that what's most important is short-term rainfall intensities that were not considered, that climate variables do change and they do affect the hydrodynamism, and the soil has changed. And in some cases, that's changed a lot. So this motivates to understand how can we look at what has been designed and how are things happening now, and to see how should we address this problem. And based on this, we designed a research project between two entities, the University of Minho. Here we have a research group on hydraulics and environment that has been addressing highway and urban runoff for maybe 3 decades. And we have been addressing not only quantitative problems like this one, but also quality problems. And we have been studying the way of implementing nature-based solutions, because highway runoff is an intermittent and difficult runoff, and also how can we address flood flows in highways. And in other partners was Ascendi, that is responsible for 630 kilometers of highways in Portugal and does asset management, intensive asset management that has more than 1,200 bridges and 1,800 culverts. So they do a quality control plan based on visual inspection, and we thought that we could have the following research question. How does the design criteria that was considered for the existing culverts perform over the highway lifespan with all those changes in variables that I just talked about? So this project has started in 2022. We are at maybe 30% of the project. Master thesis has already been concluded that addressed what the main variables that address these changes. And we are at this time studying statistically analysis on not only the national network of precipitation, but also specific rain gauges that were installed along the highways that were not used until now. So different time frames are being analyzed, and we have selected a case study that has been focused, alarmed with several problems. And the next phase, we are going to develop a model and see how these variables are going to perform. So this is ongoing now. We have selected the case study. We are doing statistical analysis on all the data of precipitation on different timescales. We have also studied what methodology was used on the projects, and it was mainly the same methodology, just considering the flow proportional to the area, the type of occupation of the soil, and the intensity. And in all of them, the intensity was used based on the values that are given on our regulation that is from 95. So data is more than 30 years old, and this is one of the things that we want to address. So we are studying the hydrological process that motivate the surface runoff that appears and the fluid flows estimation. We are nextly going to develop a model where we are going to calibrate the basin, and we are going to read the flows, and we are going to compare them and see what are the main variables and how did they change through the years. So this is an ongoing project. We are still doing some hard work on the statistical analysis, and the most interesting parts are going to be developed in the next month. And we are hoping that with this result, we are going to have a simple method that, based on the change of soil and precipitation patterns, we can signal what are the culverts that will be more interesting to model and to do a series of concerns based on the changes that have occurred on the land and on the precipitation. Thank you very much.
Paulo, very interesting study again that we are improving. The next presentation will be done by Bahit Zhu, which she will talk about in infiltration capacity evaluation of porous pavement.
Good morning, ladies and gentlemen. My name is Chu Longjia. Zhu Baihe is our PhD student. I'm from Chang'an University, China. This is the topic today, the lab study of clogging and cleaning of porous pavements. The contents for today's presentation includes the introduction and the description of the proposed approach, the lab simulation program, and also I will present the clogging and maintenance results and followed by the conclusions. The permeable pavement is very common in our daily life due to its advantages of reducing peak stormwater, replenishing groundwater, improving traffic safety, reducing traffic noise, and also it can help us to mitigate urban heat island effects. The advantages of porous pavement depend very much on its porous structure, but this one is very easy to be clogged by dust and debris during its daily life, and hence it's very important to evaluate the clogging characteristics and cleaning effectiveness of porous pavements, because it can help pavement engineers to make maintenance plans in order to maintain a high porosity level for porous pavements. But there are some issues encountered during the process of evaluation of clogging characteristics and cleaning effectiveness of porous pavements. For example, it's very hard to monitor clogging process of in-service pavements, and also inconsistency involved in testing approaches, and also uncertainty of effectiveness of cleaning methods. Therefore, a set of lab procedures is needed to evaluate the effectiveness of cleaning, and this is also the focus of our study. The infiltration flow, it does not follow our traditional Darcy law. From this figure, we can see that the relationship between the flow speed and the hydraulic gradient varies as described in this figure. To address the permeability issue in porous pavements, therefore, in our study, we adopt this modified Darcy law. The equation shown here is the modified Darcy law, with V stands for flow velocity, K stands for hydraulic conductivity, I stands for hydraulic gradient, and N is the experimental coefficient. There are different ways to clean a porous pavement in our daily life, including a high-pressure water washing, the vacuum cleaning, and also combination of these two methods. Because the high-pressure water washing is the most commonly used way to clean the porous pavement, and this is also the way adopted in our study to clean our specimen. And for the cleaning threshold level, in our study, we consider 3 levels, which is 50% of initial hydraulic conductivity of porous pavement, 25% of initial hydraulic conductivity, and 0.3 millimeter per second. This is the flow chart for our experimental clogging cleaning the test program. So in first step, we need to measure the initial hydraulic conductivity K0 of our specimen and subject them to the clogging treatment. After each cycle of clogging treatment, we have to measure the hydraulic conductivity. If the pre-selected maintenance threshold level is not reached, we continue with our clogging treatment. And if the pre-selected maintenance threshold level is reached, we perform our cleaning treatment to our specimen, and we also need to remeasure the hydraulic conductivity. And we repeat the whole procedure until the specimen has reached its terminal permeability. And at this point, we can stop our experiment. This is the whole flow chart for our study. And this is the gradient used to prepare for our porous mix used for different initial porosity level, 15%, 20%, and 25%. So the specimen prepared has a diameter of roughly 152.4 millimeter and a height of 95.3 millimeter. This is the lab permeability, the measurement setup. So the test cylinder has a diameter of 150.2 millimeter. And this is the clogging procedure we adopt in our study. So first step, we need to place our test specimen to the experimental apparatus and apply 5.3 grams of the residual soil evenly on the top face of the specimen and keep the specimen at a constant head of 450 millimeter for 5 minutes to achieve a stable infiltration rate. And this table shows us the target grades of residual soil. And now I will introduce our cleaning procedure in our study. So first, we need to also keep a specimen at a constant head of 450 millimeter for 5 minutes to achieve a stable infiltration rate. And use the high-pressure water machine, which involves a handheld water gun with an outlet nozzle diameter of 6 millimeter and adjustable the water pressure to flush our specimen and strike the surface of the specimen at an inclination of 45 degrees and a water pressure of 2.5 ampere for 30 seconds. And the last step is move clockwise until the entire top surface was cleaned. And this is the cleaning procedure we followed in our study to clean our clogged specimen. So now I will show you the clogging and the cleaning test results. This slide shows us the hydraulic conductivity, the decreasing trend of the hydraulic conductivity without any cleaning measures. These three curves shows an changing trend of hydraulic conductivity with an increasing number of clogging cycles for different initial porosity level. So for specimens with initial porosity level of 25%, 20%, and 15%, they have their hydraulic conductivity reduced to almost zero after being clogged for 12, 10, and 8 times respectively. And this regression equation shows a deterioration trend of hydraulic conductivity. This equation, Kn, stands for hydraulic conductivity of the specimen of clogging cycle. And alpha beta, they are constant value, and N stands for number of clogging cycles. So this table shows us the test results without any cleaning measures for the beta value. So the larger value of beta, the faster the hydraulic conductivity of the specimen deteriorates. For the PA25, it has the largest initial permeability coefficient and maintains high permeability throughout the surface life of the permeable pavement. And conversely, PA15% has the smallest. The largest the porosity of the larger the porosity of the specimens, and the smaller the beta value. This is the finding from our results. Setting different maintenance threshold level may result in different maintenance cycles. So this slide shows us the experimental results caused by setting the same maintenance threshold for specimens with different initial porosity level. We take this picture as one example. For the specimens, they have 3 initial porosity level, which is 25%, 20%, and 15%. And if we choose one, the same maintenance threshold level, which is 50% of the initial hydraulic conductivity, we will find that the pavement performance is better for the specimens with a higher initial porosity level. And if the specimens with the same initial porosity level, and we choose different levels of the maintenance if we choose the different maintenance threshold, and we can see this example, the initial porosity level for these 3 specimens is 25%. And we choose 3 maintenance threshold level, which is 50% of K0, 25% of K0, and 0.3 millimeter per second. So from the result, we can see that the higher maintenance threshold level will result in a more frequent maintenance cycles. So now I will show you the test results of clogging and cleaning. The permeability coefficient of the porous mix gradually decreases with increasing clogging cleaning cycles, and the higher the permeability of the porous mix, the longer the service life with the same plan of maintenance cleaning threshold, and the greater the average infiltration capacity maintained over the entire service life. The high initial permeability of the porous mix can reduce its maintenance cycle, i.e. Single cleaning can maintain a longer service life. And the higher the cleaning threshold, the higher the average permeability during the service life of the porous mix, but more clogging cleaning cycles are required to maintain the required permeability performance while reducing its service life and increasing maintenance costs. This slide shows us the continuous cleaning can extend its pavement service life. For this blue line, it indicates the permeability variation trends without any cleaning measures, and this red line indicates the permeability variation trends after the different cleaning cycles. And this table shows us the test results of beta after different number of the cleaning cycles. So the value of beta, it shows an increasing trend with the increase of cleaning cycles for the same plan. And the larger the porosity, the smaller the beta value with a given cleaning threshold. And the higher the set cleaning threshold, the slower the rate of deterioration of the permeability. And finally, we come to the last part, conclusions. So a lab procedure for introducing clogging in porous mix and evaluating the effect of high-pressure water cleaning was proposed in our study. The clogging for porous felt and hydraulic conductivity, the measurements were performed using self-developed apparatus, and the cleaning treatment was performed using a high-pressure water machine. And the porous asphalt with higher initial permeability would have a longer service life, and the effect of each cleaning would last for a long time period. The use of higher cleaning threshold levels result in higher average permeability performance throughout the entire service life, but increases maintenance costs. The decay rate of hydraulic conductivity was characterized by beta value in this study, and beta value increases with the increase of cleaning cycles and decrease of porosity and cleaning threshold. This is my end of that is my end of slides. Thank you.
For another very interesting presentation. Moving to the third one. I'm sorry if I mispronounce your name, Tusboy Sadaviro. Okay. Development of a new index for evaluating the partial subsidency of porous asphalt surface layers. So, floor is yours. Thank you.
Hello everyone. I belong to Nippon Expressway Research Institute Company Limited, 高速道路総合技術研究所 in Japan. In Japan, the porous asphalt pavement has been used since 1998 and has become a standard surface material for expressways in Japan. As the porous asphalt pavement has a high porosity, it functions to drain rainwater from the surface layer quickly. As a result, driving safety in rainy weather is improved, and the number of traffic accidents has been greatly reduced. Furthermore, since it also functions to absorb noise generated by vehicles, it makes it possible for passengers to travel comfortably and reduce noise for people living along the road. As stated above, while the porous asphalt pavement has many advantages, it also has its disadvantages. Damaged cold striping, where the asphalt peels off from the aggregate and reduces the adhesive strength of the aggregate, caused by rainwater infiltrating through the surface course, has occurred in the binder course beneath the surface layer formed by the porous asphalt mixture. If this type of damage occurs, partial subsidence will often appear on the surface course of the pavement. This photo shows subsidence at the outer wheel pass and swelling at the outer rain line. In the sample of the right, you can see striping in the binder course beneath the porous asphalt layers. This partial deformation is distinctive to porous asphalt pavement. That was not seen when dense grade pavement was mainstream of surface layers pavements. Next. In Japan, the evaluation index for the road surface is amount of rutting, cracking rate, and International Roughness Index, IRI. These indexes are calculated based on the data obtained by the road surface conditional measurement vehicle. These indexes were established before the porous asphalt pavement became mainstream. Deformation requiring repair of porous asphalt pavement in recent years are shown in this figure. Repairs for rutting, cracking, and IRI, which are items of management criteria, take up some 65% of the total number of repair works, followed by those for potholes and pumping, which take up 30%. And potholes and pumping often occur after the occurrence of partial subsidence. Therefore, it is necessary to create a new index for evaluating partial subsidence of porous asphalt surface. The new index uses the transverse profile measured by the road surface condition measurement vehicle to calculate rutting. The transverse profile is measured at 10 mm intervals in the transverse direction and at 50 mm intervals in the longitudinal direction. Assuming that the incline of the transverse profile's approximate line is the horizontal gradient, the incline is corrected to 0. This is figure A. Next, to put the longitudinal gradient to 0%, the height of the approximate line is set to 0 meter. This is figure B. By performing this process on all transverse profiles of reference height 0 mm will run in the longitudinal directions, resulting in three-dimensional point group data with the road surface gradient corresponding to 0%. To aggregate the amount of change in the three-dimensional point group data of the road surface, the standard deviation of the road surface height in the range marked by a square framework calculated. The standard deviation of the road surface height was color-coded to better visualize the partial subsidence of the porous asphalt pavement. This figure shows the standard deviation threshold corresponding to the color and a rough image of the road surface. This figure shows photos of the road surface and colored map placed side by side. It can be seen that partial subsidence areas are their precursors corresponding to the color traces. The standard deviation of road surface height calculated from three-dimensional point group data is related partial subsidence. Based on the above, we developed a new index 5 meter sigma max for evaluating partial subsidence of porous asphalt surface layers. This index is the standard deviation of the maximum road surface height within a 5 meters section. A comparison of the new index and repair records for potholes, pumping, and other damage found during routine inspections revealed the relationship shown in this table. If 5 meter sigma max is 1 to 2, the road surface is low risk. It is unlikely that there will be visible deformation on the road surface after 1 to 2 years. If 5 meter sigma max is 3 to 4, the road surface is medium risk. It is likely that there will be visible deformation on the road surface after 1 to 2 years. If 5 meter sigma max is 5 or over, the road surface is high risk. There is already visible deformation on the road surface. The table shows the breakdown of high-risk sections. It can be seen that the very large pothole has developed when 5 meter sigma max was 8 or over. Finally, I would like to introduce our current initiatives. We continuously monitor the medium-risk sections on the expressway and observe the progress of deformation. In the future, we plan to calculate a new index again when visible deformation occurs on the monitor section. This concludes my presentation. Thank you for your attention.
Another way, in this case, a field evaluation of the porous asphalt. And then the last but not least, Jose Jimenez will be presenting the development of porous cement concrete. Oh, you're going to present it for him? Okay. With waste emulsion materials for road pavements.
Okay.
So we'll have, he couldn't be here, so Jorge is going to be presenting in his behalf.
Okay, thank you, Gerardo. Good morning, everyone. So, this work is the PhD of my students, as Jimenez from Timor East. Is not in Portugal, so I'll try to present the results that he put here in this paper. The paper deals with the development of a porous cement concrete, not asphalt concrete, but cement concrete, to be applied not in Portugal, but in Timor East. And the objective is not to develop a conventional cement concrete, but a cement concrete with vast demolition aggregates. So this presentation has 4 parts: introduction, materials and methodology used for development, results, and final conclusions that we got. So, in terms of the objective or the introduction of this work, the main objective, as I said, is development of a porous cement concrete using vast demolition aggregates. And for this type of materials, the main objective is the functional properties, not the structural properties. In fact, the cement concrete pavement have extremely exigent requirements in terms of structural properties, because the pavement life is extremely huge compared to the asphalt pavement. But the most properties that we are trying to implement are the functional properties, main drainage for this case, because we are talking about a porous cement concrete, but roughness, texture, and friction, and also mechanical properties. And I have one or two slides about mechanical properties of this material. So we use natural aggregates, and the demolition, vast aggregates from demolition of construction that in Timor East is a problem that they are trying to solve, and they are trying to put in the roads. There, the pavements are not asphalt pavement as we have here in Portugal. Most of the pavement there are cement concrete pavements, and the objective is put that demolition vast inside the pavement, in this case in cement concrete materials. For development of this cement concrete, we follow the regulations or the indication that we have for asphalt concrete in terms of aggregate gradation, because if you are trying to develop a porous material, the most important factor that we must take into account is the grade gradation. And because it's the grade gradation that has porous, where we can put the water inside the material. So we follow the regulation that we have in Portugal for porous concrete asphalt, and we use this gradation 12.5 millimeters that follow the ASTM standard for N89 and N8 gradation. So we are inside the international laws. So the development of this porous cement concrete was developed in two steps. In the first one, we developed a conventional cement concrete, a porous cement concrete, and after that developed where we follow every rules for the properties of functional and mechanical properties. In second step, we had the vast of demolition. So in this paper, we don't present the first step of this development that we use for the reference material. But we present mainly the results of the influence of the vast demolition that we put inside the cement concrete. So in terms of material, we have four materials, the reference one, and one with 10% of VAS, another one with 20%, and the last one with 30%. This is design of these four materials. The first one without without VAS, and the other one with that percentage. This is the aspect of the cement concrete. As you can see, we have a lot of pores for the water entrance, and as you can see, it looks like asphalt, a porous asphalt concrete. The only difference is the color, but as a first aspect, we can see that this is a porous material and probably perform well when we put in the road. We produce a lot of specimens for a lot of tests, and we produce slabs for permeability, for the evaluation of the functional properties in terms of roughness, texture, slip resistance. We produce also specimens for mechanical properties, and at our left-hand side we can see beams for the evaluation of dynamic model and fatigue resistance. In terms of fatigue resistance, I don't have results here because we are finishing the analysis of those results. So in terms of methodology, we carry out all tests necessary to evaluate the functional and structural properties of this material for these four porous cement concrete, and the main tests are here, divided by tests for fresh cement concrete, where we have the VB test, permeability test, compressive and flexural strength. And in terms of functional, we evaluate the sand paths, texture, friction, and for mechanical performance, we evaluated the dynamic models. So the most important property for porous cement concrete is permeability, and for that evaluation we produced two apparatus. The first one following the Spanish law, and we developed also another that followed the falling head permeability test. So we evaluated the permeability of the cement concrete using these two types of tests. We also measured the porosity of the cement concrete, compare the density of the material to the maximum density, and also using the image from the specimen filled with a very thin material with different colors to have a contrast in the image, as you can see. So if you look only to the surface, you can see some porosity that we have in this material. So in terms of results I start with the fresh cement concrete, and we can see that when we put the vast material, that is different from natural material, because the natural aggregate, they are almost a rounded shape, and that is sometimes is completely different from the vast material, where we have a complex shape, and the main influence of that shape is probably the reduction of the porosity of the material, and also the compactability of the material. So we can see, based on the VB test, that the presence of the vast does not influence the compactability of the cement concrete. In terms of permeability, the first columns of this graph were collected from the bibliography, and only the black columns are the results of this work. So as you can see, we are inside the range of the values that we found in literature. So in terms of permeability, we can say that we have a good result for all cement concrete that we test, not only the G1 with the vast material, but the reference one. In terms of the structural properties, we evaluated compressive and flexural strength, and we are almost in the same range when we compare the material with the vast component to the reference, except for 10%. I think we had some problem with these specimens, but if we remove this outlier, they are almost in the same range of the reference material, both in terms of compression and flexural strength. In terms of the texture, we evaluate it by two different ways. The first one was the sand patch, and the results are quite good, extremely good. We have values greater than 1 millimeter, and we can goes up to more than 2 millimeters. And we evaluate, and we evaluate also the texture by comparing the scanning of the specimen surface, and you can see that the texture is extremely interesting for this type of material. In terms of friction, we got also interesting values that are compatible with cement concrete material, mainly with porous materials, and the values are around 70 and 80, and the influence or the presence of the vast does not affect the global value of these parameters. So we can say that we have a material that can be applied in the road without any problem in terms of friction. In terms of mechanical properties, we evaluate dynamic models, and we have here the results. We evaluate also the fatigue resistance, but we are finishing the analysis of those results. But in terms of dynamic models, here we have a problem. It's clear because it's a porous material. It's not a complete fill material, so the dynamic mold goes up to 15,000, and it's supposed to have values around 25, but this is not a complete fill material. This is a material with a lot of voids. In terms of voids, we are talking about 25%, so 25% of the material has zero dynamic modes. But the results are relatively interesting for this type of material. The main consequence is when we design a road pavement with this material, we must put this value that in fact as for the material. So, in terms of conclusion, this work allow to validate the use of construction and demolition vast in the development of a porous cement concrete that, in terms of functional properties, follow every requirement that we need for a pavement surface, and this type of vast does not affect the main properties of the material except the structural one, but in terms of functional, we think that we have an interesting material. Thank you.
Jorge, we have a few minutes maybe for a few questions if anyone has any.
Thank you. Actually, I have a few questions. First question is to Mr. Sadahiro. You speak about rutting. This rutting, is this caused by the loosening of material, or is it by a deformation of the top layer? I have the impression that when you speak about rutting, that you actually mean raveling. That is, there is losing material, which would be more consistent with the material that you describe, porous asphalt. So normally it does not deform very quickly because it's a stony skeleton. So, but isn't it material that's loosening, and that is you have kind of ruts? Do you understand the question?
I am a co-author of him. So thank you for asking our research. So due to aggregate type of aggregate, if it easy to strip, this road will be deteriorate about rotting or other type of deterioration. In Japan, stripping of asphalt is the most common rotting reason. Yeah. Yes.
Now you're here. I had a question for Mrs. Zhu about the porous asphalt. When you clean the porous asphalt with high pressure, water under high pressure, do you see any damage? Because that's what we had once a test track with the 2-layer porous asphalt, and we cleaned it with high pressure water, and then we saw that we had a lot of stones that loosened from the top layer. So that's maybe a problem with the cleaning procedure that you presented.
Thank you. For us, actually, we don't encounter this problem because we use the inclination for 45 degrees. Yeah, so there's no damage for the surface.
Since you're here, I would ask you a question too. Have you done any verification of between the lab testing and some in situ sections in the field? No? Okay. Any other questions?
I've got a question for Mrs. Pinto about you propose the co-financing because you've got those toll roads and they're closed and you can charge people. What I was thinking first of, and maybe that's a completely ridiculous idea from an economical standpoint, but would it be an idea that, because most of the pollution comes from the tires, that you just add a tax to the tires, that everybody who buys a tire, instead of like 50 euros a tire, you pay 60 euros and the 10 euros go to whatever you need? Or is that a stupid idea? Except that suddenly everybody will start buying their tires in Spain and not in Portugal, but
Thank you for your question. It's not at all, but it would control for the, not all pollution is due to tires use, so it would not control for all the others. In addition, you are not linking the use of the highway to the price, because you can buy the tires and do not drive on highways. So one disadvantage of that system is that the payment is not related to the use, but is related to a related subject. But it can be, I mean, we are taxing for carbon footprint of products in the same logic. So it could be an alternative, but it's not linked to the damage of the use of the highway, but is linked to a related product. So it has that disadvantage. True, true, true.
Just a question for you. I've experienced for the cost, for the willingness to pay for reducing noise. There was a study of Nabrud, and in a group, a working group of European Commission, and I was part of that. We discussed the results because Portugal was the member state of Europe with the lower willingness to pay in the case of noise. They declare 9 euro for 1 dB for a year, and in contrast with Switzerland, that is 100 euro for 1 dB 1 year. So this kind of study show a large distribution considering many other parameters like the economical level and the capacity, obviously, of the country. But in this case, how much was this willingness to pay in terms of money? I mean, in terms of euro for something?
It's not on euro, it was a percentage increase on the toll that they were paying. So the average percentage increase was 163, if I remember correctly, percentage points. So if you are paying 5 euro, which is a very small short of the highway, would be paying 5 plus 1%. Yeah. I'm lucky because the co-author is here, so I'll pass it to him.
Well, most studies have identified the main groups of pollutants. So one is solids that have metals, some metals absorbed. The others are nutrients, and the other ones are heavy metals. The heavy metals, the zinc come from tires, as you spoke. Yeah, copper comes from the brakes. But we haven't seen a lot of studies that identify micropollutants in highway runoff here in Portugal. Okay.
It's a very large problem. So it's difficult to measure because it's the size of microplastics, there are few techniques that.
We have seen studies that identify rubber, but as it's in the total solids, TSS. So the fraction, they study the fraction, but not as a category inside the plastics as micropollutants.
Okay, we can continue the discussion during lunch because we are a little bit behind. I want to, maybe we join me in thanking again for the author for the presentation. And I think we'll move right away to the closing section.
So before going really to the closing session, we have a parenthesis, which is our awarding moment. So I was the one that was invited to do and have this privilege to award our participants about their performance here, the young participants that I must remind. And well, I thank our evaluators for being so attentive and doing this difficult job. We have one winner almost in each session, so we have 8 winners. So they will get a diploma, so an award certificate, but not only that. So the ones that will get the award are invited for the next symposium, and they have a free registration. So it's an incentive to keep going with this and show their work going on. So I will ask the winners to get the award. I'm sorry, but I will not ask for the first name, the first one, because I can't pronounce the name, sorry. Just the first words, which is Ajay, and for the work development of high-fidelity staggered-type pavement interaction model for skid resistance analysis.
Since he's not here, I'll collect on behalf of him.
Okay.
Thank you so much.
Thank you. And the second one is, I can pronounce the name now, Filippo Balzano. Is he here? And I call also Ira Segundo. The next one is João Afonso. And also call Kazuya. Kazuya, yeah. Now, Manuela. Oh, congratulations. Obrigada. Orlando. From our last session, so what? So all, of course, and we will now go to the closing session. Thank you.
Dear colleagues, my dear friends, as you know, we are reaching the end of our symposium after 3 very intensive days, both in terms of scientific and technical activities and social events. I'm sure that as a result, all of us will return to our institution, to our homes, greatly enriched. And in this context, I'd like to acknowledge the contribution of all those who helped this symposium to be a success. First of all, I'd like to thank all participants who have attended all sessions, the main reason for this symposium. Secondly, a special word of appreciation for our keynote speaker. Thank you very much, Professor Foy. And for our invited speakers, as well as for all the authors who have contributed to the high quality of this symposium. Particular thanks to all support institutions and, in particular, our sponsors companies, which have contributed with their decisive financial support to make sustainable our program. A success event is also the result of the efficiency and accuracy of the secretarial support, as well as of the operational network of internet, sound and video. For all staff involved, my special thanks. Last but not least, I would like to thank in particular 2 colleagues. Professor Foy, for his support from the beginning of the preparation of this PFDM edition, and my co-chair Elizabeth, who was decisive for all components of this symposium until the very last minute. Thank you for you. Before closing, our symposium, I'd like to invite Professor Kumar Anupam from the Delft University of Technology to share with us the news related to the next, in this case, 3rd edition of our symposium. Professor Kumar.
Yes, very good afternoon. And at first, I would like to promise that I won't be for long between you and your lunch, so I'll be very quick. I have a very short announcement video. Yeah, I would like to congratulate the whole organizing team for hosting such a beautiful event. So I think we all echo that it was a wonderful event and we shared joy or knowledge together. And next, I would like to thank the steering committee, Professor Pereira, who has given us an opportunity to host the next event. Yes, so without further ado, I would like to invite you all. Please come to Delft and we'll be really happy to host you there. This is a small announcement video, exactly 5 minutes.
Dear colleagues, dear friends, now I declare this symposium closed, wishing you all a safe return to your places. Now I'm inviting you to a short walk, 15 minutes maybe, to have lunch at the Oriental restaurant in the city center town. And again, I'd like to thank you all for being the most contributors to the success of this symposium. Thank you very much.
Remark, so the restaurant is a Torau, just right in the center, and it's called Oriental, okay? But we are going walking so we can follow each other.
Yeah.